Imagine a galaxy so bizarre, so mathematically improbable, that every rule we thought we knew about how galaxies form shatters the moment you look at it. A perfect golden core floating in space, wrapped in a flawless ring of blue stars, separated by a massive empty void. This is Hoag's object, a cosmic riddle suspended 600 million light-years away, and the deeper scientists look, the stranger it becomes. From impossible symmetry to age-defying star populations, nothing about it should exist. Yet there it is, quietly mocking our understanding of the universe. A galaxy in a halo. The first glimpse of Hoag's object. In 1950, Arthur Hoag, an American scientist, used the 48-inch Schmidt telescope at Palomar Observatory to look at the stars. At first, there didn't seem to be anything strange about it, just another faint object among many others. After a while, he saw something strange on his picture plate. A bright, round ring around a small, thick center. At the time, he thought it might be a planetary nebula, which is a star's dying gas ring that stays bright. That made sense. A lot of planetary nebulae have round shapes. But something didn't seem to make sense. This ring was too big and bright, and the core in the middle looked too much like a close-together galaxy. Hoag was careful not to jump to conclusions. Back then, astronomers didn't have the benefit of modern space telescopes or high-speed computers. To confirm what something was, you had to rely on photographic images, careful measurements of brightness, and a lot of patience. Hoag noted its location in the constellation Serpens and recorded its unusual structure, but he didn't have the tools to fully investigate it. The image became part of his 1950 paper, but he described it as a ring-shaped galaxy, or possibly a planetary nebula. The mystery was officially born. As years passed, the photographic plates of Hoag's object became a curiosity among astronomers. Other galaxies were often messy, spirals with uneven arms, irregular galaxies scattered with bright knots, or elliptical galaxies with fuzzy shapes. But this, it looked like a painting done with a compass. The ring was so clean and symmetric that some thought it must be an optical illusion, a photographic defect, or even a trick of perspective. It wasn't until the 1960s and 70s, with better telescopes and more advanced spectroscopy, that astronomers began to suspect that Hoag's object was truly something extraordinary. Measurements showed the light from the ring was coming from stars much farther away than any planetary nebula. The redshift revealed it was a galaxy, located about 600 million light-years from Earth. That meant the ring itself was enormous, tens of thousands of light-years across. Planetary nebulae are tiny in comparison, just a few light-years wide. Arthur Hoag himself had no idea that the object he stumbled upon would go on to puzzle astronomers for decades. He wasn't even searching for unusual galaxies. His research focus at the time was on different types of celestial structures. But sometimes, science advances because someone notices something odd in the corner of a photograph. This was one of those moments. Another thing that was clear from the early pictures was that the space between the bright ring and the center core looked eerily empty. Galaxies generally have a smooth change from the center to the arms or ring around the outside. Stars and gas clouds fill in the spaces between the two. It looked like the middle had been erased here. The image was so clear and sharp that it didn't match any known type of galaxy at the time. Throughout the 1980s and 90s, as larger ground-based telescopes and CCD imaging improved clarity, Hoag's object became a kind of odd cousin in galactic classification. It didn't fit as a spiral. No arms, no bar, no visible disk. It didn't fit as an elliptical. The outer ring was too bright and too sharply defined. And it wasn't like other ring galaxies, which usually showed signs of violent collisions, streams of debris, and uneven ring shapes. The strangest thing, it looked like it wasn't being bothered. When you see a ring galaxy in the sky, it's usually because two galaxies crashed into each other, sending waves of gas and stars to the sides to make a ring. But Hoag's object didn't have any scars, tidal tails, or clouds of scattered stars that would suggest that something like that had happened. It was there all the time. Wonderful. When the Hubble Space Telescope took a high-resolution picture of Hoag's object in 2002, it was already known as a strange object in space. The Hubble picture confirmed its shape, an oval core that is golden and densely packed, surrounded by a nearly perfect blue ring of young, hot stars. There was a dark space between them that almost didn't have any stars visible. Even stranger, a smaller ring galaxy that looks a lot like the main one can be seen in the background of the Hubble picture. This strange coincidence added to the mystery of the object. For Arthur Hoag, the discovery was an unexpected legacy. He retired from active astronomy before the full mystery of the object was recognized, but his name would forever be attached to it. What began as a faint, strange-looking spot on a photographic plate became one of the most famous "how is this possible" cases in extragalactic astronomy. The perfect ring a shape galaxies shouldn't make. Many people think of spirals, with beautiful arms spreading out from a bright center, or big, smooth ellipses when they think of galaxies. The truth is messier. Spiral arms often stick together and aren't straight. Galaxies that are elliptical can be uneven or long. It sounds like ring galaxies would be neat and round, but they're not always perfect rings. A lot of the time, they're bent, broken, or twisted, making them look more like a splash in a pond after a few stones are added. It's not just a ring, which is why Hoag's object is so strange. It's almost perfect. It's so orderly that it looks fake. The outer structure of Hoag's object is a smooth, unbroken loop of bright blue stars. When astronomers measure its circularity, they find deviations so small they're almost negligible. That's practically unheard of in astronomy. The universe is full of forces that disrupt order. Gravity from nearby galaxies, the uneven pull of dark matter, even the messy nature of star formation itself. For a galactic ring to remain this precise means something unusual is at work. Ring galaxies typically form when one galaxy punches through another, setting off ripples of star formation in a ring shape. The Cartwheel Galaxy is the textbook example, a sprawling, uneven wheel with bright knots of young stars scattered across it. But unlike the Cartwheel, Hoag's object's ring doesn't have the telltale asymmetries of a collision. There are no tidal tails of gas and stars flung into space, no distortions, no lopsided regions where the collision was stronger on one side. The ring's width is also quite interesting because it stays the same. In some rings, the areas where stars are being formed tend to group together, leaving brighter areas where gas is heavier. There is a very even width in Hoag's object, like it was drawn with a cosmic drawing compass. Astronomers can see that the ring's shape is smooth because the brightness doesn't change much from one side to the other. Not only is this beauty nice to look at, it's also a science pain. Chaos rules the forces that form galaxies. Gravity pulls in strange directions, gas clouds fall apart randomly, and stars tend to form in spots. It's like watching a storm build a perfect sandcastle, all those forces working together to make something this orderly without a clear way to guide them. Some scientists have wondered if the symmetry could be maintained by a kind of resonance, a pattern in the orbital paths of stars and gas that naturally locks them into place, similar to how Saturn's rings are kept sharp by the gravitational tugs of its moons. But unlike Saturn, Hoag's object has no obvious shepherds, no companion galaxies close enough to be sculpting its shape. The orientation is another strange thing. From our point of view, the ring is facing almost straight ahead. In other words, we're looking straight down at it, with not much tilt. That doesn't happen very often, according to statistics. The views of most galaxies we see are skewed, making them hard to focus on. It's like flipping a coin a dozen times and getting heads every time to see one that is well matched. It makes the puzzle even more difficult to solve. Astronomers have used computer modeling to try to figure out what shape the ring is. There are different starting points for these models, such as a collision, a gravitational resonance, or even the idea that the system could be shaped by a strange ring of dark matter. But the models almost always come up with rings that are a little oval, have uneven shine, or are full of dust and debris. All of them are not the same as Hoag's object's perfect circle. If the perfection were only in appearance, one might dismiss it as coincidence. But spectral analysis, the study of the light coming from different parts of the ring, shows that the motion of its stars also follows an unusually uniform pattern. The orbital velocities are consistent across the entire structure. In other words, the symmetry isn't just skin deep, it's built into the motion of the stars themselves. This consistency opens up scary options. One reason is that the galaxy has been alone for a very long time, which has allowed its structure to settle down without any outside interruptions. But over millions of years, it should have been warped by things inside the galaxy, like the uneven pull of its own gravity. Another reason is that the ring is pretty new in cosmic terms. It formed not long ago, so it hasn't been disrupted yet. Then where is the proof of the event that made it? Some astronomers have even joked, half seriously, that it looks too perfect, as if it were engineered. Of course, there's no evidence for anything artificial about Hoag's object, but the comment reflects just how out of place it feels among the universe's usual chaotic creations. The perfect shape of Hoag's object's ring makes it stand out in lists of galaxies. It has the kind of structure that makes you stop when looking at pictures of the stars, because your mind says, that can't be natural. Still, as far as we know, it is a cosmic puzzle in the form of a perfect loop. The golden core, an elliptical heart inside a ring. A thick golden sphere of stars that looks like a small elliptical galaxy is at the center of Hoag's object. It seems almost as unlikely as the ring that surrounds it. It's not as important as the bright blue ring, but it's still there. As it turns out, most of the galaxy's visible mass is in the core. Its color shows that the stars inside are very old, much older than the stars in the ring around it, and their light is warmer, like that of an old person. Elliptical galaxies, by nature, are collections of older stars packed into a rounded shape, often formed through ancient mergers. They tend to have little gas or dust, which means they're not actively making many new stars. Hoag's object's core fits that description almost perfectly, and yet it sits in the middle of one of the brightest, bluest, most star-forming rings ever observed. That contrast between the dead heart and the vibrant outer ring is one of its biggest oddities. Spectroscopic studies show that the stars in the core have a much higher average age than those in the ring, in some cases billions of years older. This suggests that the core existed long before the ring formed. That raises an obvious question. If the ring came later, what process surrounded this old elliptical heart with such a youthful, active structure? The core's structure is unusually smooth. There are no dust lanes winding across it, no clumps of gas, no irregular patches. In many galaxies, even old elliptical cores show scars from past mergers, faint shells, ripples, or streams of stars that hint at their violent history. But here, the golden sphere is pristine. If a collision created the ring, why did the core escape without visible damage? On top of that, the core's light profile, that is, how its brightness changes from the center outward, doesn't match what would be expected for a galaxy with that much mass. It's a little more concentrated than I thought it would be, like something squeezed it together a long time ago. There is, however, no sign of recent gravity compression from a close collision. It's possible that the core is what's left of a small elliptical galaxy that moved in close to a bigger spiral galaxy and caused the ring to form before losing its outer stars. But that doesn't explain why the effect is so clean, like it was done by a surgeon. Another idea is that the ring could have been made of gas that came from a long-lost partner galaxy and was pushed into orbit around the core. If that's the case, the gas would have had to settle into a very stable and even orbit, which is much easier to guess than to prove. The golden light of the core also provides a chemical clue. Stars in this region tend to be richer in heavier elements, what astronomers call metallicity. This suggests the core has gone through multiple generations of star formation in the distant past, with earlier stars enriching the gas that formed later ones. But those enrichment levels don't match the chemistry of the outer ring, implying that the two regions didn't share the same star-forming history. It's almost as if they belong to two separate galaxies that somehow became one. The fact that the heart doesn't rotate might be the most surprising thing about it. It has been seen that the center elliptical moves less quickly than predicted. Many galaxies, even older ones, have measurable spin because they still have the motion from when they were first formed. When it comes to Hoag's object, the ring around it spins much faster. This difference suggests that the two systems may have come from very different places and are now stuck together in a way that seems to work well. Astronomers have attempted to model how an old elliptical core could remain so undisturbed while being wrapped by such a perfect ring. Most simulations fail because the same event that creates the ring, such as a collision or a gravitational encounter, should also disturb the core, adding visible distortions. That hasn't happened here. The fact that the golden core is so smooth suggests either the ring formed through a process that doesn't involve major violence, or that any disturbance happened so long ago the core had time to completely relax back into shape. Hoag's object is one of the most beautiful galaxies in the known universe because of the difference between its two parts. The warm golden sphere shines like a source of old starlight, and the electric blue ring goes around it like a crown of light. They don't blend together because there's that strange gap between them. It's almost like they're being nice and keeping their space. Stars without a bridge, the empty gap. What isn't there in Hoag's object is one of the most disturbing things about it. There is a wide, strangely dark area between the burning golden core and the bright blue ring. It's tens of thousands of light years wide, but there aren't many stars in it. Even in galaxies with clear structure divisions, there are usually stars, scattered groups, or faint clouds of gas in the space between the main features. This place is almost completely empty, like a moat separating two heavenly castles. Scientists were surprised by how clean this gap is when they first looked at it in depth. Not only are there not many bright stars, but also not many weak older stars. The Hubble Space Telescope's deep pictures showed that this void isn't just because the stars are too dim to see. It's almost as if something had swept the area clean, because the number of stars here is much smaller than what was predicted. In a typical ring galaxy formed by a collision, the gap between the core and ring is filled with turbulent leftovers, streams of stars, clumps of gas, and chaotic debris. The Cartwheel Galaxy, for example, has a busy interior between its core and outer ring, with knots of activity scattered throughout. Hoag's object, by contrast, looks as if an invisible boundary has been drawn, keeping the two regions from ever blending. It's possible that orbital mechanics keep the gap open. If the gas and stars in the ring are moving in very stable synchronous orbits, they may simply stay away from the space close to the core. This is kind of like how the moons of Saturn keep some parts of Saturn's rings clear through their gravitational pull. But in Hoag's object, there isn't a clear moon or other object that acts as a guardian. The gap might also have been caused by a big event that cleared the area a long time ago. A big blast of energy from the core, maybe from a giant black hole that was there a long time ago, could have blown out the gas and stopped stars from forming in the area. Over time, space would become empty because there would be no gas to make new stars. There is a problem with this theory, though. We don't see much proof that a giant black hole is actively affecting the galaxy right now. There isn't a bright active galactic center, any jets, or any strange X-ray activity. Chemical studies add another layer to the mystery. The few stars that are detected in the gap don't share the same chemical fingerprints as either the core or the ring. They appear to be remnants from an even earlier time, suggesting that this region might be a kind of fossil zone, the leftovers of a structure that existed before the ring formed. This raises a provocative question. Was Hoag's object once a completely different type of galaxy that was somehow transformed into the strange structure we see now? The emptiness also creates a gravitational puzzle. The core and ring exert forces on each other, and you'd expect that over millions of years this would cause stars and gas to drift inward or outward, slowly filling the void. But the gap remains sharp, as if some stabilizing mechanism is constantly reinforcing the separation. Models attempting to simulate this stability often require finely tuned conditions that seem unlikely to persist naturally for so long. One thing that makes Hoag's object look so strange is the gap between them. The golden sphere of old stars doesn't fade into the ring around it slowly. Instead, there's a sharp, almost surgical cut-off. With such clear lines between the galaxies, they appear man-made, like they were built instead of evolving naturally over time. Even though no serious expert says it's fake, the way it looks is disturbing in how real it is. In a world where chaos is normal, this lack is a very loud quiet. The gap makes it harder for us to figure out how galaxies move matter around, change over time, and keep their shapes. If the ring and core really have different histories, they were made in different times or from different sources, then the gap could be a sign of their union that will last forever, a place where no one has been able to settle for hundreds of millions of years. Even now, telescopes can't fully resolve what's inside the void. It may contain faint streams of dark matter, invisible to our instruments, holding the region in place without adding visible light. Or it may simply be a gravitational dead zone, where conditions for star formation have been impossible for eons. Whatever the reason, this empty bridge is as much a defining feature of Hoag's object as the ring or core themselves, a mystery in negative space. The mystery of the ring's formation. The bright blue ring around Hoag's object is more than just pretty. It's a puzzle wrapped around a galaxy. There aren't many rings in space to begin with, and when they do appear, they almost always have a clear history. Most are what's left over after something big has happened, like a smaller galaxy slamming into the disk of a bigger one, sending waves of dust and stars outward. Others are caused by gravity resonances, which have a slow but steady effect and can shape the paths of stars into designs that repeat. Unfortunately, Hoag's object will not fit any of these models. The first idea experts came up with was the well-known collisional ring situation. This model says that a small neighbor galaxy would have crashed through the core of the main galaxy, compressing the gas and starting the formation of stars in a ring. What's wrong? There are scars in every collisional ring we've seen. There is space junk all over the place. The ring isn't all the same thickness, and there are signs that the invader galaxy is close by or already joining. There is none of that in Hoag's object. The ring is a uniform shape, and its width is the same all the way around. There is also no clear suspect nearby to take the credit. Another idea was the resonance ring model. In spiral galaxies, stars and gas can get trapped in resonances, specific orbital patterns caused by the gravity of a central bar structure. These resonances can pile up material into rings over millions of years. But Hoag's object doesn't have a bar, or even the spiral arms where such resonances usually occur. The core is an elliptical, smooth, rounded, and lacking the disk structure needed to make this mechanism work. Some astronomers wondered if the ring might have been formed by the gradual accretion of gas from the galaxy's surroundings. In this cold accretion model, streams of intergalactic gas could have spiraled in, settling into a rotating disk far from the core, where it eventually formed stars. While this could explain the lack of a visible collision, it's still hard to understand how incoming gas would arrange itself into such a perfect uniform ring without forming more irregular structures first. A more unusual idea is that the ring's symmetry could be due to the galaxy's dark matter halo, which is the unseen mass that surrounds all galaxies, being particularly smooth and round. If the dark matter is spread out just right, it might be able to guide the gas and stars into a safe path around the Sun. But it's extremely hard to map dark matter halos, and there's no direct proof that Hoag's object's halo is different in this way. The age difference between the core and the ring also complicates things. Observations show the core's stars are ancient, while the ring stars are much younger. This means the ring is a later addition to the galaxy's life story, not something that formed alongside the core. In a collisional model, the timing would have to be precise. The collision would need to be recent enough for the ring's stars to still look young, but long enough ago that the ring could settle into perfect symmetry. Also, the ring moving around adds to the puzzle. Spectroscopic readings show that the stars in the ring orbit in a strangely ordered way, with not much scattering of their speeds. Not only are they moving in the same general direction, but they are also moving in almost similar circles, as if someone had put them there on purpose. It is rare for models of ring formation to show such consistency. Usually, there is turbulence for millions of years after a creation event. But this ring looks calm and grown up. Some scientists have looked beyond the familiar for explanations. One speculative idea is that Hoag's object might be the product of a gentle merger, where a small galaxy was absorbed so slowly and evenly that it didn't leave behind the usual chaotic traces, but instead contributed its material to the ring in a stable pattern. Another proposes that gravitational waves from some ancient event might have triggered star formation in a perfect shell around the core, though this remains purely hypothetical. Each theory does answer some questions, but it also brings up new ones. Collisions show how rings work, but they don't show how perfect they are. That's why there is symmetry, but not why there is no bar. Gas accretion can explain why stars are so young, but not why there are no patterns. And there is still no proof for the dark matter ring idea. This is why the formation of Hoag's object is still one of the biggest puzzles in the study of galaxies beyond our own. Some theories are called into question, but not just one. It's almost like the galaxy was made to resist classification. It sits in a quiet part of the universe with a structure that shouldn't be there but clearly is. No evidence of a collision. Astronomers first look for signs of a past crash when they see a galaxy in the shape of a ring. That's because most of the ring galaxies we know about got their shape when two galaxies crashed into each other straight on. The usual story goes that a smaller galaxy intrudes into a bigger galaxy's disk, sending waves of gas and stars outward in the shape of a ring. Over time, these waves cause new bursts of star formation, which makes the outer loop bright. It's a reliable model, one we've seen happen in many systems. The Cartwheel Galaxy is perhaps the most famous example. Its ring is patchy, uneven, and surrounded by wisps of scattered stars and gas, all evidence of a violent past. But when astronomers turned their attention to Hoag's object, something didn't fit. For a supposed collision ring, it's missing every obvious clue. First, there's no visible debris. In a galactic smash-up, the gravitational chaos flings material into space, forming tidal tails, long, faint streams of stars, and distorted shapes. Hoag's object has none. The space around it is unusually clean. No tails, no arcs, no messy knots of gas drifting away from the ring. The lack of these features suggests either there was no collision, or if there was, it happened so long ago that every trace has faded, which contradicts the youth of the ring's blue stars. Second, there's no sign of the culprit. In most ring galaxy systems, the intruder galaxy is either still nearby or already merging with the core. Hoag's object sits in relative isolation. The nearest significant galaxies are far enough away that they couldn't have been recent impactors. And deep sky surveys haven't uncovered any small, stripped-down remnant that could be the remains of a long-absorbed intruder. Third, the symmetry is wrong, or rather, too perfect. Collisions are messy by nature. The intruder almost never strikes dead center, and any slight offset usually makes the resulting ring lopsided. But Hoag's object's ring is almost mathematically circular. If a collision caused it, it would require an impact so precisely aligned that the odds become almost laughable, like firing an arrow across a football field and hitting the bullseye of a moving target. The velocity data also poses a problem. In known collisional rings, the stars and gas in the ring often have a wide range of speeds as the system recovers from the shock. Hoag's object's ring, however, shows a surprisingly uniform rotation pattern, as if it's been stable for far longer than a fresh collision would allow. That means either the ring somehow settled into perfect order with unprecedented speed, or it wasn't formed in the violent way we've assumed. There is another possibility. The crash theory could still be true, but in a very strange way. Some scientists have come up with the idea of a ghost intruder situation, in which a very small gas-filled galaxy crashes into the ring and blends in perfectly with the gas there. The problem is that even a gas-filled invader should leave some visible gravitational marks, which are changes in how the stars in the core move. However, Hoag's object's core is surprisingly unaltered. There's also a chance that if there was an impact, it wasn't between two galaxies, but between Hoag's object and a huge cloud of gas. In theory, this kind of collision could cause rings to form instead of the normal starry wreckage. But this brings up a new question. Where is that cloud of gas now, and how did it spread out the stuff so evenly? Observations show that there isn't a huge gas reserve floating close. Many scientists are hesitant to put Hoag's object in the same group as the Cartwheel Galaxy or other well-known ring systems because there is no proof of a crash. It looks, acts, and lives in a way that are all too different from each other. If the impact model can't explain it, we either missed something very important or Hoag's object shows a completely different way that galaxies evolve. A cosmic isolation chamber. What makes Hoag's object unique is not only its perfect ring and strange core, but also the fact that it lives in a very empty part of the universe. Galaxies tend to be social. They stick together in groups, pull on each other with gravity, and sometimes crash into each other or join. Even though these interactions are messy, they are what make galaxies change over time. They move gas around, make new stars, and change the shape of structures. On the other hand, Hoag's object looks like it was left alone for a very long time. When astronomers chart its surroundings, they find a startling lack of close neighbors. Hoag's object sits far from any major galaxy cluster. Its nearest significant companions are millions of light-years away, too distant to exert any strong gravitational influence. The space around it is dominated by emptiness, broken only by faint, distant galaxies scattered across the background. In galactic terms, it's living in the countryside, far from the bustling city centers where galaxies constantly jostle and interact. This isolation matters because it removes many of the common triggers for dramatic galactic change. In denser regions, galaxies are constantly disturbed by tidal forces from their neighbors. Gas streams in and out, collisions are frequent, and gravitational harassment can warp their shapes. Without such influences, a galaxy's structure can remain stable for billions of years. That might explain how Hoag's object's perfect ring has survived without being pulled apart. There's simply no one nearby to disrupt it. Isolation also creates problems for the standard models of how ring galaxies form. If Hoag's object is so far from other galaxies, then the usual explanations involving collisions or tidal interactions become much less likely. There's no obvious partner that could have created the ring through a direct hit or a close pass. Even if such an interaction happened in the distant past, the intruder would have had to escape without leaving any visible trace, which is hard to reconcile with what we know about galactic dynamics. The lack of changes in the surroundings also makes the youth paradox harder to fix. Since the stars in the ring aren't very old, it's likely that the structure was made not too long ago in cosmic time. But if there hasn't been a nearby galaxy close enough in recent months to set it off, what could have caused such a big burst of star formation in a circle? Some experts think that the fact that Hoag's object is in an area with low density, which is sometimes called a cosmic void, may have had a more subtle effect on its growth. When there aren't many people in these places, intergalactic gas can flow more slowly without being stripped or heated by frequent interactions. In theory, that gas could be pushed equally into the galaxy from different directions. It would then settle into a circular path that is symmetrical, creating the ring. But the details of how such a process works are still mostly guesswork, and models haven't been able to clearly copy it yet. Hoag's object's remoteness may also be the reason it has remained so pristine in appearance. In busy galaxy clusters, even if a ring forms, it's likely to be distorted within a few 100 million years, by the gravitational pulls of nearby giants. Hoag's object may have had the luxury of evolving in near total peace, allowing its unusual structure to freeze in place without external interference. Being alone could also explain why its core doesn't seem to be affected at all. The core might stay smooth, dust-free and stable for billions of years if it doesn't have any nearby stars to stir things up or new stuff to feed on. This would make it a dinosaur relic, a well-preserved piece of a different time in the history of the galaxy, ringed by a ring that formed much later through a process that is still unknown. The quiet places where Hoag's object is found don't answer the bigger question of how its ring came to be, though. The isolation actually makes the problem worse because it takes away the most widespread reason. If you look in a pond and don't see any stones, sticks, or fish close, you might find a completely round ripple. The event must have been different from anything that could have come from a nearby star system. Astronomers continue to survey the space around Hoag's object, looking for faint traces of past interactions, maybe a ghostly stream of stars far beyond the ring, or a barely visible dwarf galaxy that could be the remains of a long-lost partner. So far, the search has turned up nothing conclusive. Double ring illusion, the background twin. Astronomers and the public were both amazed by the beauty of Hoag's object when the Hubble Space Telescope took its famous high-resolution pictures of it in 2002. A smaller, fainter, ring-shaped object was tucked inside the outer ring and far in the background of that same frame. It was an even stranger surprise. It was quickly called Hoag's twin, or the smaller Hoag. Right away, it looks like something out of this world, as if the universe were repeating itself at two different sizes in the same line of sight. The inner twin is not at all a part of Hoag's object. It is very far away, so far away that the two galaxies will never meet. The only thing that makes them look alike is that they are aligned so perfectly from our point of view. But the chances of this happening are out of this world. The background twin appears through the gap between Hoag's object's golden core and its bright blue ring. That placement makes it look almost staged, like a deliberate design choice in a piece of cosmic art. If the smaller ring were just a few arc-seconds in another direction, it might have gone unnoticed. But instead, it sits perfectly framed, a smaller echo of the main structure, peeking through the emptiness. Because it's so far away, the background twin is much harder to study in detail. Even with Hubble's clarity, it appears as a tiny smudge of light, just distinct enough to show a ring-like shape. Spectroscopic measurements are difficult, but early observations suggest it too might be a ring galaxy, though its structure could also be the result of gravitational lensing or another phenomenon. Without sharper data, its exact nature remains uncertain. Some have suggested that the smaller Hoag might not even be a true ring galaxy. It could be a galaxy seen through a patch of dust or gas that blocks its center from view, creating the illusion of a ring. But the brightness distribution seems to favor the idea of a genuine outer structure. If that's the case, it would mean we are witnessing two rare cosmic objects aligned purely by chance. From a mathematical point of view, the double ring orientation is almost absurd. Ring galaxies are already pretty rare. They only make up a very small percentage of all known galaxies. It's very unlikely that one ring galaxy will be right behind another, letting us see both of them in the same small field of view. If you throw a coin into the air, it will land on its edge twice, but on different sides of the table at the same time. The double Hoag sight has inspired both serious scientific curiosity and playful speculation. While astronomers focus on the mechanics of alignment and the classification of the background object, the public imagination runs wild. Some see it as a sign of hidden cosmic patterns, or even as an argument for the idea that certain structures might be more common than we think, if only we looked deep enough to find them. For scientists, the real value of the background twin is as a reminder of how much chance plays into our observations. If the background galaxy had been slightly off-center, Hubble's famous photo would have been beautiful but less iconic. Instead, we have a frame where the improbable became reality, offering a visual metaphor for how the universe often hides layers within layers. There's also a small prize for noticing things. Because the twin is so far behind Hoag's object, any light we see from it has already gone by the galaxy in front of us. That means it has gone through the ring of gas and maybe even dark matter around Hoag's object. In theory, studying that light could give scientists secondary knowledge about the properties of the material around Hoag's object. It would be like using nature as a backlight for a study that we could never plan. So far, no in-depth follow-up has shown us much more about the smaller Hoag. This is mostly because it is so faint that long scans are needed, and telescope time is always in high demand. Still, it's one of the strange things about Hoag's object that makes it stand out. It is a very rare and orderly galaxy in its own right, and its most famous picture is shared with what might be a cousin from very far away, seen billions of light years away. The age paradox of the ring stars. The ages of Hoag's object stars are one of the most interesting clues to its past, but they also add to the puzzle instead of solving it. The golden core is made up of stars that are billions of years old and glow with the warm yellow light that comes from stars that are fully grown. That part makes sense. Cores that look like an ellipse are usually made up of older people. But the ring is a whole different thing. Its bright blue color is typical of young, big stars that burn quickly and hot. Some of them are only a few million years old. This big gap in ages is a problem because galaxies usually have smoother changes in the number of stars in their populations. Usually, the stars get younger toward the edges as you move from older ones in the middle to the edges. But in Hoag's object, there is a sharp break between the old stars in the core and the young stars in the ring. The empty space in the middle acts as a dividing line. It looks like two different galaxy timelines were squished together into one picture. Spectroscopic studies reinforce the visual impression. By breaking the light from the ring into its component wavelengths, astronomers can identify the chemical fingerprints of different types of stars and estimate their ages. These studies show that many stars in the ring are extremely young, less than 10 million years old, while others are a few 100 million years old. This suggests the ring has been forming stars for a long time, but is still actively producing them today. The core, by contrast, hasn't formed new stars in billions of years. This raises an obvious question. If the core is old and dormant, where is the fuel for the ring's ongoing star formation coming from? Young stars require dense, cold gas clouds to form. That gas must have been collected into the ring somehow. But without nearby galaxies to donate material, and without signs of a recent collision, the source remains a puzzle. Some astronomers propose that the gas might have been slowly accreted from the intergalactic medium, the thin soup of gas that exists between galaxies. In this scenario, Hoag's object could have pulled in streams of pristine hydrogen over hundreds of millions of years, which then settled into stable orbits in the ring and began forming stars. But while this could explain the continued youth of the ring, it doesn't explain the precision of its circular shape. Inflowing gas is usually messy, leading to warped disks or irregular structures. Some people think the age difference might be because of an interaction in the past that brought in new gas but mostly left the core alone. For instance, a dwarf galaxy that is full of gas could have been shook up, causing its matter to settle into a ring and help stars form. This would explain why the stars in the ring are so young, but it's hard to be sure without seeing any leftover rocks or tide tails. The age paradox also forces us to think about timescales. If the ring formed quickly in a single event, the stars in it should be roughly the same age, with only slight variations. But the data suggest a range of ages, meaning star formation in the ring has been sustained over a significant period of time. Whatever created the ring didn't just trigger a one-time burst. It set up conditions for star formation that have lasted for hundreds of millions of years. The chemical makeup of the stars in the ring doesn't exactly match that of the core. This is a small but important feature. It looks like the ring stars formed from gas that had a different evolutionary past because they have a little less of the stronger elements. This makes it more likely that the ring's material came from somewhere else besides the core's leftovers. The paradox of age tells us that Hoag's object has two separate histories locked together in one galaxy: an old, inactive heart and a young, active halo. They're not changing at the same rate, and there doesn't seem to be a clear way to connect them, either physically or in terms of time. It's like finding a castle from the Middle Ages, exactly surrounded by the skyline of a modern city, with no sign of the ages that came before or after. No spiral arms, no bar, no disorder. Although galaxies come in many forms, they tend to stick to a few well-known trends. Spirals, which have beautiful arms that wind around a bright center. Barred spirals have a bar of stars in the middle that feeds matter into the arms. Ellipticals are mostly made up of old stars and are smooth and simple. It doesn't matter how jumbled, irregular galaxies look, they still have their own way of being structured. But Hoag's object is different. It doesn't fit neatly into any group. It's most different from other things because it doesn't have any twisting arms. In the local universe, spiral galaxies are the most common type. A lot of star formation takes place in their arms. Density waves, which are areas of higher gravity that move through the disk and squeeze gas together to make new star groups, shape these arms. The shapes in Hoag's object, on the other hand, are not twisting. The thing's ring isn't an arm bent into a loop. It's a different circle that doesn't seem to be connected to the core by a spiral pattern. It also lacks a central bar. In barred spirals, a straight line of stars stretches through the core, acting like a conveyor belt that funnels gas toward the center and helps shape the galaxy's evolution. Without a bar, the usual spiral bar dynamic is absent. In fact, Hoag's object's core is more like an elliptical galaxy, smooth, round, and devoid of the dust lanes, gas clouds, or star-forming clumps typical of spirals. And then there's the surprising absence of disorder. Most galaxies, even those that look symmetrical at first glance, show asymmetries when examined closely. A spiral arm might be brighter on one side, a dust lane might cut across part of the core, or faint tidal streams might stretch into space from past encounters. Hoag's object doesn't show these imperfections. The ring is evenly bright all the way around, the core is clean and symmetrical, and the space between them is empty. It's as though every chaotic element that usually comes with galactic evolution has been filtered out. This structural simplicity is baffling because galaxies don't usually stay clean for long. Interactions with neighbors, minor mergers, and even the uneven distribution of gas and dark matter tend to create lopsidedness over time. In theory, Hoag's object should show some scars from its past, but none are visible, even under Hubble's sharp eye. Some researchers have suggested that the lack of spiral arms and a bar could be due to the way the galaxy's mass is distributed. If Hoag's object has a particularly stable gravitational potential, possibly shaped by an unusually smooth dark matter halo, it might prevent the formation of density waves that give rise to arms. But this doesn't explain why the outer ring is so perfectly maintained while the interior remains empty. It's harder to explain why there isn't a bar. When stars in a disk galaxy react to changes in the galaxy's gravity, bars tend to form on their own. They can be found in both young and old galaxies, which suggests that they are a regular step in the evolution process. If Hoag's object had a bar at any point, it must have been erased. But erasing a bar generally leaves behind something, like a center bulge or inner ring. Neither of them is here. Another strange thing is that there are no dust roads. Spiral galaxies are made up of dark, winding strands of dust that show how they are put together and give stars the building blocks they need to form. The center of Hoag's object is free of dust, and the ring doesn't have the spots that dust clouds normally make. This lack of dust may help explain why it looks so clean, but it also means that the process that made the ring did not involve the violent, gas-filled conditions that are common for spirals. Taken together, these absences make Hoag's object something of a structural ghost. a galaxy that has shed nearly every common feature except for its core and its improbable ring. It defies the neat categories astronomers rely on, standing outside the usual spiral, elliptical, irregular framework. It's tempting to think of it as a finished galaxy, one that has settled into a final, stable state, but the active star formation in the ring suggests otherwise. It's still evolving, just not in a way that fits the standard blueprints. Whatever forces shaped it did so without leaving the usual fingerprints. The perfect symmetry problem. A picture of Hoag's object shows that the ring is almost exactly round, which stands out more than anything else. It's not crooked, stretched, or bent. It is the same width all the way around, and no matter what angle you look at it, it is always the same distance from the center. Really accurate things like that don't happen very often in astronomy, almost never. When you look at the size of galaxies, nature almost never makes forms that are perfectly round. Most ring galaxies have visible distortions. Some parts of the ring might be thicker or brighter than others, caused by uneven star formation or leftover debris from a collision. Even in systems with well-defined rings, gravity from nearby galaxies, or the pull of their own irregular mass distribution, tends to stretch the ring into something slightly elliptical over time. Hoag's object doesn't suffer from any of these flaws. The symmetry is so precise that astronomers have used it as a benchmark when testing image processing algorithms. If the software can trace a perfect circle around Hoag's object's ring, they know it's working correctly. That's how unusually clean its outline is. The problem with such perfection is that it doesn't line up with how galaxies usually evolve. Rings are dynamic structures. Their stars move, gas clouds drift, and external forces constantly tug at them. Even without a nearby galaxy to disturb it, the internal gravitational variations of the galaxy itself should cause subtle warping over millions of years. Yet Hoag's object's ring seems frozen in a state of geometric purity. To maintain that shape, the galaxy's mass must be distributed with extreme precision. One possibility is that Hoag's object has an unusually smooth and spherical dark matter halo, exerting a uniform gravitational pull in every direction. That could keep the ring's stars in stable, circular orbits. But mapping dark matter halos is notoriously difficult, and no study has yet confirmed this for Hoag's object. It's also possible that the ring was made in a single, fast event, like a perfectly aligned impact, and hasn't had much time to change shape. This idea is flawed because it doesn't fit with what we know about the universe, such as the fact that stars have been forming in the ring for hundreds of millions of years. A short-lived event should have left behind a structure that is more uneven and temporary, not one that looks stable and busy. There are some scientists who think the uniformity could be a result of the way the stars in the ring are moving. If all of their orbits are in the same plane and have very little irregularity, the ring would look like a circle from our point of view. But this brings up another question. How did so many stars end up moving in such a straight line? Galaxies usually have a lot of stars moving all over the place. The empty gap between the ring and the core only adds to the puzzle. In most galaxies, even those with rings, there's some spillover of stars or gas into the space between the main components. Hoag's object's gap is clean, as if the ring was placed at a precise orbital distance where nothing else is allowed to linger. This sharp division enhances the visual symmetry, but makes the mechanics harder to explain. Time is another issue. Things that are very stable tend to lose their balance over billions of years. Small pushes from gravity, gas flows, or star movements change the shape over time. So, if Hoag's object has kept its perfect shape for a big part of its life, then something is actively keeping it that way. It's still not clear if that's because of dark matter, the balance of orbital resonances, or some other unknown force. This desire for perfection is what keeps Hoag's object at the center of the discussion. When scientists try to use known physics to explain it, they have to choose between keeping the symmetry and being able to explain how stars are being formed in the ring, or the other way around. It seems like the galaxy is where two impossible events meet, and both of them have to be true at the same time. The missing dark matter clues. Dark matter has been one of the most effective tools in science for many years. We can't see it, but we can feel how it affects us. Most galaxies have dark matter that can be seen in the way that stars and gas move. This is especially true in the outer parts of the galaxy, where visible matter alone can't explain the speeds that can be seen. Astronomers can get a rough idea of how much dark matter a galaxy has by comparing its visible light to the movements of its stars. But with Hoag's object, the results haven't been so straightforward. Its rotation measurements, the speeds at which stars in the ring and core move around the center, don't perfectly match the patterns we'd expect if the galaxy had a standard dark matter halo. In many galaxies, rotation curves stay flat or even rise slightly at large distances from the center, a sign that dark matter's gravitational pull dominates in the outskirts. Hoag's object's data suggests something different. The ring stars aren't moving as fast as expected for a galaxy of its size, as though the dark matter halo is weaker or shaped in an unusual way. One theory is that Hoag's object's dark matter halo is not as dense as usual. This means that it has less of this unseen stuff compared to its gas and stars. It is thought that ring galaxies need strong dark matter halos to keep their shape, so that would be very strange. If there wasn't enough dark matter, gravity instability would make the ring bend or break apart over time. But Hoag's object's ring is solid and even. It's also plausible that the dark matter is spread out in a different way than normal. In a lot of galaxies, the halo is circular and has a smooth density that rises toward the center. But Hoag's object could have a halo that is flatter or less even, or it could have an edge that is particularly sharp, which would change the paths of its stars in strange ways. This might also help explain why the space between the core and the ring is so clean. If the gravity field there isn't stable for star motions, then matter wouldn't be able to stay there. Some astronomers have even speculated that Hoag's object could be an example of a galaxy where modified gravity, an alternative to dark matter, might need to be considered. These theories suggest that our understanding of gravity itself changes at very low accelerations, removing the need for dark matter in certain cases. While controversial, Hoag's object's odd rotation profile is exactly the sort of anomaly that makes scientists test these ideas. What complicates the problem is that dark matter is also involved in how galaxies acquire and retain gas. The dark matter halo's pull on gas keeps it from leaving in most galaxies, which keeps star creation going. How has Hoag's object managed to gather and maintain the gas that drives the ring's ongoing star creation if its halo is weaker or has a different shape? If the dome wasn't there, the ring might have broken apart a long time ago. The galaxy's seclusion adds another element to this enigma. Hoag's object should be a pretty clean place to study the spread of dark matter, since it is not near any galaxies that could affect it. There is an idea that this makes it easier to measure because we don't have to take into account the pull of our neighbor's gravity. Now, even with that benefit, the data still doesn't fit into the usual halo model. Hoag's object is situated at a distance of approximately 600 million light-years, which contributes to the challenge. It's harder to get very accurate speed readings at that distance, especially for faint stars in the outer ring. Astronomers use the movement of gas clouds as markers, but these readings can be thrown off by things like the winds that make stars or small changes in the past. We might have a better idea of the galaxy's true dark matter profile when we get new telescopes, but for now, the numbers don't give us much confidence. Hubble's 2002 high-resolution study. When the Hubble Space Telescope looked at Hoag's object in 2002, it had already been interesting scientists for more than 50 years. But earlier pictures taken from the ground were amazing for the time, but they were missing the fine details needed to figure out what they were hiding. That changed right away with Hubble's high-resolution view. It made an image of the galaxy that was so clear and even that it became one of the most famous pictures of the early 2000s. It also sparked a new wave of interest in science and the public. Before Hubble, Hoag's object appeared as a blurry core surrounded by a faint ring, its edges softened by the limitations of Earth's atmosphere. The basic structure was visible, But the finer points, the even spacing of the stars in the ring, the emptiness of the gap, the pristine nature of the core, were hidden in the blur. With Hubble's advanced optics and its position above the atmosphere, those details came into sharp focus for the first time. The 2002 images revealed that the ring wasn't just a vague band of light. It was composed of thousands of hot, young blue stars packed into a narrow zone, their combined glow outlining the ring like a neon halo in deep space. The width of the ring was surprisingly consistent all the way around, and the distribution of star clusters was remarkably even. No clumping, no visible disruptions. The core, too, came into sharper definition. Instead of a messy central bulge, it appeared smooth and golden, its older stars blending into a flawless sphere. There were no dust lanes slicing across it, no obvious star-forming regions, and no irregularities to hint at recent turbulence. This smoothness was part of what made the Hubble image so captivating. It was a galaxy that looked almost manufactured in its perfection. The background twin, the smaller, farther away ring-shaped galaxy that was perfectly lined up in the space between the core and the outer ring, was one of the most surprising things that Hubble's picture showed us. It was very small and faint, but it duplicated Hoag's object structure in miniature, making it look like a double-ring galaxy. People talked about how statistically unlikely it is for things to line up in this way, which made the picture go viral. Aside from being beautiful, the pictures gave experts useful information. Astronomers could improve their predictions of stellar ages by examining the colors of the stars in both the core and the ring. The yellow tones in the core showed that it was made up of older, cooler stars, while the bright blue light in the ring showed that it was made up of huge, short-lived stars that were only a few million years old. The big difference in age and color made it even more mysterious how the two buildings came to be and changed over time. The level of symmetry seen in the Hubble images also made it possible to test theories about the galaxy's formation. For example, if the ring had formed from a collision, astronomers would expect to see signs of distortion, uneven star formation, or faint tidal debris, none of which were present in the high-resolution data. This absence of expected features pushed some researchers toward alternative explanations, like resonance patterns or unusually stable gravitational environments. Hubble's study didn't solve the riddle of Hoag's object, but it made the puzzle sharper. The clean lines and flawless geometry seen in the images forced scientists to confront just how rare such a structure is. Many proposed scenarios failed simply because they couldn't produce something so perfect without leaving behind telltale scars. The pictures also changed culture. A lot of people saw them in astronomy outreach programs, textbooks, and internet groups. They were often used to show how beautiful and strange the world is. Some people who had never paid much attention to galaxies before were amazed by how symmetrical it was. For some, Hoag's object was the first time they heard of the idea that objects in space can be both natural and amazingly beautiful. The gas halo mystery. The mystery of Hoag's object lies in the invisible halo of gas that circles the galaxy, not in the bright blue ring or the golden heart. Scientists have found a large area of hydrogen gas that goes far beyond the outer ring. It is faint, but radio telescopes that are precise enough can measure it. That might not seem strange by itself. A lot of galaxies have gas halos. We expect Hoag's object's ring to act in a certain way, but it doesn't. In most galaxies, especially those actively forming stars, the gas halo is dynamic. Streams of gas flow inward, fueling starbirth, while other streams are pushed outward by stellar winds, supernova explosions, or activity from a central black hole. These inflows and outflows give the halo a patchy, turbulent structure, with hotspots where gas is being compressed and voids where it's been blown away. Hoag's object's halo, by contrast, looks remarkably smooth and undisturbed. The gas halo doesn't show obvious signs of motion toward or away from the galaxy. Spectroscopic studies measuring the Doppler shift of hydrogen emission lines find very little net movement in either direction. That means the gas isn't clearly feeding the ring star formation, nor is it being ejected in powerful flows. It just seems to sit there, extended in a calm bubble around the galaxy, like a mist frozen in place. This is a problem for our models of how galaxies sustain star formation. The outer ring of Hoag's object is still actively producing young, massive stars, which require a steady supply of dense, cold gas. If the halo isn't delivering that gas to the ring, where is the fuel coming from? Some astronomers speculate that small amounts of gas may be trickling in gradually, too subtly to detect directly, but even that would require an unusually stable transfer process to avoid disturbing the halo's shape. The size of the gas cloud is another unknown. Estimates show that it goes far beyond the visible ring, sometimes reaching 2 to 3 times the diameter of the main structure of the galaxy. That's a huge amount of space for a galaxy that looks like it's all by itself. It's not clear how Hoag's object got such a huge gas store in the first place, if it didn't have nearby galaxies that could add extra gas through tidal interactions. The smoothness of the halo also hints at an absence of violent events in the recent past. In many galaxies, mergers or close encounters leave clear marks in the gas distribution: streams, shells, or irregular clumps. Hoag's object's halo has none of these, suggesting it hasn't been significantly disturbed for hundreds of millions of years. This level of stability might help preserve the ring's perfect symmetry, but it also makes the galaxy harder to explain in terms of typical ring formation scenarios, which usually involve some kind of disruptive event. Some researchers have floated the idea that the halo could be a remnant from an earlier stage in the galaxy's life, perhaps left over from the time when the ring itself formed. If the ring was created by a massive inflow of gas, whether from a merger, a captured gas cloud, or a resonance effect, the leftover material could have spread outward to form the current halo. Over time, the more chaotic parts would have settled, leaving behind the calm structure we see today. But if that's the case, it raises another question. Why hasn't more of that gas fallen inward to fuel even more star formation? The halo's strange behavior might also have something to do with Hoag's object's dark matter spread. If the dark matter ring is a strangely smooth spherical shape, it might help keep the gas envelope stable by spreading out the gravity forces evenly. The gas might not be falling in too fast because of this too. It might be held in a state of balance by gravity pulling it in and pressure pushing it out. The metallicity puzzle. In astronomy, metallicity is a measure of how many elements heavier than hydrogen and helium a star or gas cloud contains. These heavier elements, called metals in astrophysics, are forged inside stars and spread into space when those stars die. Over cosmic time, successive generations of stars enrich a galaxy's gas with more and more metals. That's why older stars generally have lower metallicity, while younger stars tend to form from metal-rich gas. Hoag's object, however, doesn't quite follow this rule. Studies of its ring's metallicity have revealed something strange. The young blue stars in the outer ring have a chemical composition that doesn't match what we'd expect if they formed from the core's enriched material. Instead, their metallicity is significantly lower than that of the core's stars, resembling the chemical signature of gas that has had a very different evolutionary history. This is important because it shows that the ring wasn't just made by pushing the inside gas outward. What if that were true? The gas in the ring would also be high in metals because it would have come from the same place. The low metallicity instead points to a source outside the galaxy, new gas that came from there. It's possible that Hoag's object caught a huge cloud of almost pure hydrogen from the space between galaxies. This would explain both the lower metallicity and the fact that stars are still being formed in the ring. It's hard to explain, though, how such a large amount of gas could be captured without any clear signs of disorder, like tidal tails, imbalances, or debris. Another concept is that the ring might be what's left of a gas-filled dwarf galaxy that Hoag's object ate up. In this case, the dwarf's gas settled into a circle around the core and started to make stars. This could fit the chemistry seen because small galaxies tend to have less metal than bigger ones. But once more, this idea isn't supported by enough data. The stars from such a dwarf aren't visible, and the ring's perfect symmetry doesn't fit with how merger remnants usually look. The metallicity puzzle gets even more interesting when you look at the distribution of metals within the ring itself. Observations show that the metallicity is relatively uniform all the way around, rather than being patchy or showing gradients. In most galaxies, metallicity tends to vary depending on location, reflecting the complex history of gas flows, star formation, and supernova feedback. Hoag's object's ring appears almost too even, suggesting that whatever process brought the gas there mixed it thoroughly before star formation began. This level of chemical uniformity is hard to achieve without turbulence or rotational mixing, and yet, the ring doesn't show signs of being stirred up by violent processes. That implies a gentle, controlled settling of gas into the ring, which again clashes with the high-energy events that are usually invoked to explain ring formation. There is another problem with the metallicity data. The stars in the ring don't have as much metal as the stars in the core, but they aren't very basic either. They still have stronger elements in them, like oxygen, nitrogen, and iron. This means that the gas they formed from had already been through at least one generation of star formation. That rules out the thought that the gas is truly primordial, meaning it hasn't changed since the Big Bang. However, it does leave open the question of where it came from and how it got to be arranged in such a strange way. There is a difference in the amount of metals in the core and the ring, which some scientists think could help us figure out how old the galaxy is. If the core formed early in the past of the universe and got rid of most of its gas, it might have stayed chemically stable for billions of years. Later, a new flow of less enriched gas could have formed the ring, giving the galaxy two different histories of its history. Along with other proof that the core and ring are not only different in shape, this idea makes sense. The core's rotation secret. Scientists who study galaxies often find that the center parts move at the same speed as the structures around them. When it comes to spiral galaxies, the bulge and arms rotate in a way that is similar to each other. But when it comes to elliptical galaxies, the whole system tends to move as one, though it is less organized. In a small but important way, Hoag's object breaks this rule. The shining ring around its golden center spins much more slowly than the core itself. This was found by measuring the changes in the Doppler shifts of the light from stars in both areas. It looks like the stars in the ring are moving around the galaxy at the same speed as a disk that is actively spinning. The spinning curve flattens out to a crawl in the core, though. It's as if the galaxy's heart is moving more slowly than its outer shell. This difference isn't just a strange thing, it's a clear sign that the core and ring may not have come from the same place. If the ring had formed naturally as an extension of the core's own disk, we would expect their rotation speeds to be linked, with the core providing the gravitational anchor for the ring's motion. Instead, the ring's faster rotation suggests it might be orbiting around not just the core, but the galaxy's broader dark matter halo, while the core itself plays a smaller role in controlling the dynamics. The heart might be the remains of an older elliptical galaxy, which rotates more slowly than disk galaxies. If Hoag's object was formed as an oval shape at first, and the ring was added later, maybe by capturing an outside gas storage, then the difference in spin would make sense. The old core would continue to rotate slowly, while the new ring would move at speeds set by the bigger gravity structure. The smooth change from the slow-spinning core to the fast-spinning ring is another interesting feature. In many galaxies with parts that don't fit together right, there's a zone in the middle where the two movements mix, making structures twist or star paths go off in strange directions. There is none of that in Hoag's object. There is a clear separation between the two regimes because the space between the core and the ring is mostly empty. They may be rotating in very different ways because they aren't physically connected to each other. They aren't touching strongly enough to sync up over time. Researchers have pointed out that the slow core rotation could also be linked to its pristine, dust-free appearance. In galaxies, gas inflows often spin up the core over billions of years, both by adding mass and by exerting gravitational torque. Without a steady supply of gas, the core's rotation can stagnate. Hoag's object's gas supply appears to be concentrated entirely in the ring and surrounding halo, leaving the core to evolve passively and slowly. The slow spin also has implications for the galaxy's central black hole, if one exists. In many galaxies, the rotation of the core helps feed material into the black hole, fueling bursts of energy that can be seen across the electromagnetic spectrum. In Hoag's object, the lack of such activity, it's unusually quiet in radio and X-ray wavelengths, could be a result of the core's sluggish motion, which doesn't deliver gas efficiently to the center. There's a lingering question about whether the core's rotation rate has always been this low. If the ring was formed relatively recently on cosmic timescales, say within the last billion years, there might not have been enough time for gravitational interactions to speed up the core. Over the next few billion years, as the ring and core subtly tug on each other, their motions could begin to align. If so, we may be looking at Hoag's object in a rare transitional phase, caught between two different dynamic states. The galaxy's odd isolation may have kept the slow spin going for a long time. Since there aren't any close galaxies to push on the core, there's nothing to move its rotational momentum around. This might make it possible for it to stay in this almost separated state forever, like a fossil from its earlier days, with a much more active shell around it. Ring starburst without a trigger. There is a clear reason why starbursts happen in most galaxies. They are strong bursts of star formation. If a smaller galaxy crashes into a bigger one, the gas could be squished together into thick clouds that spark the birth of new stars. Or, tidal forces from a close pass with a neighboring star could push gas inward, causing many stars to form quickly. However, in Hoag's object, the bright blue ring is busy making new, big stars without any of the normal signs of a trigger event. Spectroscopic studies reveal that the ring is rich in hot, short-lived O and B-type stars, the kind that burn bright and die young, often within a few million years. Their presence means star formation in the ring is not just ongoing, it's vigorous. Yet when astronomers look for the typical clues of what might have set off this activity, they come up empty. There's no evidence of a recent galactic collision, no streams of stellar debris, no distorted shapes, no asymmetrical clumps in the ring's structure. The galaxy is in a remarkably isolated patch of space, making a close encounter with another large galaxy extremely unlikely in the recent past. Even the smaller background twin galaxy, seen in Hubble's famous image, is far behind Hoag's object, with no gravitational connection. So where is the fuel for this starburst coming from, and why is it arranged so perfectly in a ring? One idea is that the gas-fueling star formation has been part of the ring for a long time, perhaps billions of years, and is only now condensing into stars. But if that were true, the ring should show signs of gas depletion over time, with bursts tapering off. Instead, the activity is spread evenly, suggesting a steady replenishment of star-forming material. There's also a chance that the ring is a kind of self-sustaining structure. As new stars and supernovae form, they can send shock waves through the space around them. These waves can sometimes cause more stars to form in nearby areas. If the structure of the ring naturally sends these shock waves around its edge, it could set off a feedback loop that keeps the process going without the need for an outside signal. Still, this doesn't answer the question of how the ring was set up to allow such a stable loop in the first place. The metallicity of the ring's stars, as discussed earlier, also plays a role here. Their relatively low heavy element content suggests that the gas is either from an external, less enriched source or has been relatively untouched by multiple generations of star birth. Low metallicity gas cools less efficiently, meaning it resists collapsing into stars unless something gives it a push. That makes the ring's ongoing activity even more surprising. It's as if the galaxy found a way to coax stubborn gas into forming stars at a steady rate. The galaxy's dark matter ring is another thing to think about. If the halo is unusually round and smooth, it might make a stable gravitational environment for the ring that lets gas clouds circle without getting messed up. Over time, the ring's small instabilities or density waves could sometimes squeeze the gas just enough to make new stars. There would be no violence or short-lived events like a crash in this process. It would be gentle and last a long time. There's also the interesting but untested idea that the ring's starburst could be caused by an interaction we can't see. For example, a very small companion galaxy that is too faint for our current sensors to pick up could be moving through the ring and sending out waves of compression. If such an object existed, it would be very dim and almost perfectly lined up so as not to mess up the balance of the ring. Possible resonance ring formation. The beautiful ring on Hoag's object might have formed through a process called orbital resonance. This is one of the more captivating ideas about how it appeared. When different parts of a galaxy, the paths of stars and gas clouds, or even nearby celestial things, interact in a way that makes their motions match up, this is called a resonance. This synchronization can focus matter in certain areas, making patterns like rings or gaps. This is something we can see in Saturn's rings, which are caused by resonances with its moons. Applied to galaxies, resonance rings usually form when a rotating bar or spiral pattern inside the galaxy exerts a periodic gravitational tug on the surrounding stars and gas. Over time, material gets trapped at certain orbital distances where the pattern's rotation and the star's orbital periods line up. The trapped material piles up, forming a ring. In Hoag's object, however, the situation is more puzzling. For resonance to work in the traditional sense, the galaxy needs an internal structure, like a bar or spiral arms, to drive the process. Hoag's object has neither. Its core is a smooth, dust-free sphere, and there's no sign of an internal bar that could be shepherding gas into a ring. Without that driver, the standard resonance ring model doesn't fit neatly. A number of researchers think that the resonance might not have been caused by something inside the star, but by something outside the star. For example, a small galaxy may have passed close by a long time ago, and its gravity pulled on Hoag's object just enough to set up the circular pattern. The perturber would have to be long gone by now if that's the case, leaving only the ring as proof of its presence. This ghost resonance idea is interesting because it doesn't need a continuous bar or spiral pattern, but it's hard to show without finding the person who did it. It's also possible that the vibration is caused by the dark matter ring around the galaxy. If the halo has a strange density profile or a small imbalance, it might change the paths of stars and gas in a way that makes rings more likely to form. There is a lot of theory in this area because dark matter is invisible but has real gravitational effects. And in cases like Hoag's object, where normal theories don't work, it's tempting to look for answers in things that can't be seen. A big challenge for the resonance theory is that it typically produces rings with some irregularities. In most observed resonance rings, you can spot brighter clumps where star formation is more active, or slight differences in thickness around the circumference. Hoag's object's ring, by contrast, is eerily smooth and consistent. If resonance is at work, it's producing a level of symmetry that's virtually unheard of in other galaxies. Computer simulations have tried to reproduce this effect, but so far they struggle. When you set up a galaxy with a smooth core and try to generate a ring purely through gravitational resonance, the result is usually a lopsided or slightly warped structure. To get something as perfect as Hoag's object, the simulations often need to start with very specific, finely tuned initial conditions. The kind that make astronomers wonder if we're looking at an extremely rare, one-off event rather than a repeatable process. The resonance theory remains on the table because it does account for one important detail: the stability of the ring over time. If the stars and gas are locked into resonant orbits, they can maintain their positions relative to one another for billions of years, avoiding the collisions and dispersal that would otherwise blur the ring's shape. This could explain how Hoag's object has stayed so pristine for so long, even in the absence of recent external influences. What's missing is direct proof, like a pattern that can be measured in how the stars in the ring move, that fits with what a resonance model says should happen. In the future, instruments with higher precision and more power than Hubble might be able to find this kind of pattern. But for now, the resonance theory is just an idea that hasn't been proven with a smoking gun. If resonance really is the answer, Hoag's object would be one of the most extreme and maybe even the only examples of this effect. That would make the puzzle even bigger, since we would have to give up yet another good idea for how this perfect galaxy ring formed. The lens galaxy theory rejected. People who study astronomy first heard about Hoag's object around the middle of the 20th century. One of the first theories was that it might not even be a strange galaxy, but an illusion caused by gravitational lensing. When a big object, like a galaxy or galaxy cluster, bends light from behind it, making arcs, rings, or multiple images, this is called gravitational lensing. An Einstein ring is a nearly perfect circle of light that can sometimes be made when everything is lined up perfectly. Hoag's object looks like it could be one of these cosmic optical tricks. A bright central lens surrounded by a flawless ring of light is exactly what you might expect from an Einstein ring. The idea seemed tempting. Maybe the golden core is a closer galaxy, and the ring is actually a distorted view of a more distant galaxy's light bent around it. This would have been a neat, well-understood explanation that required no exotic physics or 1 in a billion galactic formation scenario. As soon as astronomers studied Hoag's object in more detail, the lensing theory began to unravel. The first blow came from spectroscopy. When scientists measured the light from the core and the ring separately, they found both had the same redshift, meaning they're at the same distance from Earth. If the ring were from a background galaxy, its redshift would be significantly higher, reflecting its greater distance. Instead, the data showed that the ring and core are physically part of the same structure. The inside features of the ring were another nail in the coffin. Gravitational lensing can stretch and make faraway things bigger, but it can also warp them. You could see lines of light, designs that repeat, or details that are smeared. Its ring, on the other hand, has star groups that are clearly defined, evenly spread, and not distorted. This is what you would see if you looked at the ring directly, instead of through the distorted lens of gravity. For gravity lensing to make such a perfect, thick, and uniform ring, the lensing mass in the middle would have to be very large, much bigger than Hoag's object's small, circular core. Usually, clean Einstein rings can only be made by galaxy groups, or giant galaxies, with very large dark matter halos. The heart of Hoag's object doesn't have enough mass to bend light in this way on this small of a scale. Another point against the lensing idea is the empty gap between the core and the ring. In an Einstein ring, the light is bent around the lens, but there's no requirement for a clean void in between. Often you'd see additional light from the lensed object spilling toward the center. In Hoag's object, the gap is truly empty of stars, which matches the idea of a physically starless zone, not an optical illusion. The theory also had trouble explaining the galaxy's motion. Observations of the ring's rotation show that it's moving in a way consistent with it being bound to the core by gravity. In a lensing scenario, there would be no such connection. The background galaxy's light would not move in sync with the foreground object. The matching dynamics were one of the final pieces of evidence that proved the core and ring are part of the same galaxy. The lensing idea was mostly dead by the time Hubble took a picture of Hoag's object in 2002. The clear picture showed not only the evenly spread star clusters in the ring, but also the faint structure of the twin galaxy far behind Hoag's object. This showed that the image looks very different from the galaxy's main structure when gravitational lensing is present. Radio silence, a lack of strong emissions. Astronomers don't just look at galaxies in visible light, they also listen for radio waves. Radio waves can show things that aren't visible, like how stars are formed deep in dust clouds, how black holes shoot out jets of energy, or how the faint hum of neutral hydrogen gas spreads through a galaxy. Radio waves make many ring galaxies shine brightly, especially those that are making stars very quickly. This is because of the powerful events going on inside them. Hoag's object, on the other hand, is surprisingly quiet. Radio surveys have detected only faint emissions from Hoag's object, and those signals are far weaker than expected for a galaxy with an active star-forming ring. Normally, massive young stars in such a ring would end their lives as supernovae, accelerating cosmic rays and producing strong synchrotron radiation, a hallmark of vigorous starbirth. Yet in Hoag's object, the radio brightness is barely above the detection threshold. This lack of strong radio output is puzzling for several reasons. First, it suggests either the rate of massive star formation is lower than optical images imply, or the supernovae are somehow less efficient at producing cosmic rays. The bright blue color of the ring indicates plenty of hot, short-lived stars, so the first explanation doesn't seem to fit. That leaves the possibility that the galaxy's environment is somehow suppressing the usual chain of events that leads to radio emission. At least one idea says that Hoag's object has a weaker interstellar magnetic field than most galaxies. A lot of the synchrotron radiation that can be seen at radio wavelengths comes from cosmic rays spiraling along magnetic field lines. Even if supernovae are happening at the normal rate, the radio emission would go down if the field is especially weak. This is because fewer cosmic rays would be caught. Magnet fields in galaxies are extremely hard to measure, but Hoag's object could become a great example of how these fields affect a galaxy's radio voice. It's also likely that the gas in the ring is spread out in an odd way. In many starburst areas, thick pockets of gas and dust keep the energetic particles from supernovae in check, which raises the radio output in the area. If Hoag's object's gas is spread out more evenly, these particles might be able to escape into space between galaxies before they give off a big signal. This fits with other strange things about the galaxy, like the straight line of gas in the halo and the lack of swirling in the ring. The quietness in radio wavelengths also extends to the galaxy's core. Many galaxies, even relatively inactive ones, emit at least a small amount of radio energy from their central black holes. In some cases, these emissions come from low-power jets or from hot gas swirling near the event horizon. Hoag's object shows no sign of such activity, further reinforcing the idea that its core is unusually passive. This fits with other clues, like the slow core rotation and the absence of dust lanes or gas inflows. The hydrogen line emissions that astronomers often use to trace cold gas in galaxies are faint here as well. This doesn't mean the galaxy lacks gas. We know from other observations that it has a large halo, but it suggests that much of the gas is either too diffuse or too smoothly distributed to produce strong localized signals. Again, this matches the theme of Hoag's object as a system where everything seems stable to the point of being almost static. From a bigger picture point of view, the radio silence could be telling us that Hoag's object is not only an optical oddity, but also an abnormality of more than one wavelength. Most galaxies that look as strange as this one sound strange when viewed through radio waves. This is usually because the same forces that shape their shapes, collisions, mergers, and strong gravity interactions, also send out strong radio waves. It seems that whatever formed Hoag's object was a rare, peaceful event, or at least one that happened a long time ago, so that all of its energy effects have worn off. Future radio devices like the Square Kilometre Array might be able to make maps of Hoag's object's signals that are more detailed and sharp. This could help us find faint structures we haven't seen before. They should still only show a faint whisper of radio energy on those maps. That would prove that this galaxy is truly unique, a beautiful part of the universe that values quiet over show. The ultra-smooth core. The golden heart of Hoag's object is not only unique because of its color and slow spinning, but also because it looks so clean. You can find small irregularities in the cores of most galaxies, even in elliptical galaxies that are generally calm. These can be weak dust lanes, wisps of gas, or small star groups spread out on the surface. These are the marks of internal activity, mergers, and gas flows that have happened over billions of years. But in Hoag's object, the core is so clean that it's almost scary. When the Hubble Space Telescope imaged the galaxy in 2002, its resolution was sharp enough to reveal tiny details across the central sphere. Astronomers expected to find at least some mottling, variations in brightness that indicate dust clouds or younger stellar populations. Instead, the core's surface brightness is nearly uniform, like a smooth ball of ancient stars. There are no visible dust filaments cutting across it, no pockets of blue stars, and no telltale knots of recent star formation. This kind of cleanliness is rare because galactic cores tend to be messy places. Gas from the outer regions usually drifts inward over time, feeding bursts of new star formation or fueling a central black hole. In the process, dust accumulates, shaping lanes or swirls that break up the light. Even in galaxies without active mergers, minor interactions with passing satellites can disturb the central regions. The fact that Hoag's object's core shows none of these signs suggests an extraordinary level of long-term isolation. The smoothness also supports the idea that the core may be a very old stellar population. Spectroscopic studies indicate that most of its stars are yellowish, similar to the older stars found in elliptical galaxies. If the core has not had a significant influx of fresh gas in billions of years, no new stars would form, leaving only these ancient, evenly distributed stars to dominate its appearance. The mystery is not just that the core is old, it's that it has stayed untouched for so long, despite the active, star-forming ring around it. In a typical galaxy, material from a star-forming outer disk can drift inward due to gravity, eventually settling into the core. But the vast, empty gap between Hoag's object's core and its ring seems to act like a barrier, preventing gas from migrating inward. Without that flow, the core remains a sealed-off relic of its earliest formation phase. Some people might wonder if the smoothness is just an optical effect caused by the way we're looking at it. If we look down at the galaxy's axis, we might miss some features about its structure that we could see if we looked at it from the side. But the ring's symmetry makes it very likely that we are looking at Hoag's object almost exactly side-on. This means that the smoothness is real and not just a trick of perspective. It's also possible that the core went through a period of intense action in the past that cleared it out totally. Strong winds from supernovae or a time when black holes were more active could have blown away any gas and dust that was still there, leaving only stars. With so many years between it and now, the core would have had plenty of time to become as calm and even as it is now. The catch is that we don't see any lasting signs of such an event. No shells of gas that were ejected, no shock fronts, and nothing else that would show the violence that might have made such perfection possible. This very smoothness is not just a matter of taste. It helps us figure out how the galaxy came to be. A core this clean either means that the formation process was very gentle from the start, or that any rough spots were smoothed out with surgical precision a very long time ago. In both cases, it doesn't fit well into our usual models of how galaxies form and evolve, which say that there will almost always be some amount of center irregularity. Outer ring dynamics. The outer ring of Hoag's object looks like a perfect racetrack in space from afar. It is a bright, smooth loop of stars and gas that looks like it is frozen in place. But rings like these aren't just pretty things to look at. Its stars are moving at hundreds of kilometers per second around the galaxy's center, keeping the balance of gravity just right. How does such a big, thin structure stay together for billions of years without falling apart or getting smeared into a disk? Most galaxies, especially elliptical ones, have stars in the outer parts that are part of a flat disk. The pull of visible matter and an even bigger ring of dark matter keeps these stars in place. There are more problems in a ring galaxy like Hoag's object. There is a huge empty space between the ring and the core, so the ring isn't held up by a constant spread of stars inside it. Without extra forces to keep them in place, gravity would finally push the stars closer or farther apart, which would change the shape of the ring over time. One stabilizing factor is the galaxy's dark matter halo. Observations suggest that Hoag's object is embedded in a massive, roughly spherical halo of dark matter that extends well beyond the visible ring. This halo provides an invisible gravitational framework, holding the ring stars in place along stable, nearly circular orbits. Without this hidden mass, the ring would likely dissolve within a few 100 million years. The smoothness of the ring's rotation is another clue. When astronomers measure the Doppler shifts of stars and gas around the ring's circumference, they find the orbital speeds are remarkably uniform. In other ring galaxies, small irregularities in speed can cause clumps, warps, or breaks over time. Hoag's object seems to avoid this fate, possibly because the mass distribution in its halo and core is unusually even. A symmetrical gravitational field would keep the orbits aligned, allowing the ring to remain both stable and perfectly circular. Gas dynamics also play a role. The ring contains not only stars, but also significant amounts of gas, which behaves differently from stars. Gas clouds can collide, merge, and dissipate energy, gradually settling into a common orbital plane. This process can smooth out irregularities and help the ring maintain its shape, even if individual stars have slightly different orbital paths. The catch is that this also tends to cause gas to drift inward, something that clearly isn't happening here in large amounts, or the core wouldn't be so empty. According to some astronomers, the ring may be self-regulating due to star formation feedback. When new stars are born, their winds, and eventually supernova blasts, can move the gas around the ring so that it is spread out evenly. This might keep the structure's star formation activity even and stop gas from clumping together in one place. It's possible that the stars that make the ring keep it stable over time. If that's the case, the width of the ring is much smaller than its diameter, which is another interesting fact. The fact that it is so narrow means that the paths of its stars and gas clouds are very closely lined up. In many galaxies, close objects' gravitational pull can tilt or stretch these orbits, making the ring thicker over time. The fact that Hoag's object is so far away in space may be its best defense because it can grow without being affected by gravitational nudges that would usually mess up its accuracy. Even so, simulations of galactic dynamics often fail to produce a ring like Hoag's object that can last for billions of years. In most models, either the ring collapses inward to form a disk, or it disperses into a more irregular arrangement. This suggests that Hoag's object might have started with an unusually favorable set of initial conditions, perhaps a perfectly balanced distribution of dark matter, gas, and stars from the very beginning, and has simply been left alone ever since. Why simulations fail. Computer models are a big part of modern astronomy because they help us understand how galaxies form and change over time. The known rules of physics, like gravity, the movement of gases, radiation, and the behavior of dark matter, are used in these models to make galaxies behave in different ways. In the last 20 years, these kinds of models have been able to explain a lot about the galaxy, like spiral arms, explosion regions, and ring structures that are made when galaxies crash into each other. It keeps failing when it comes to Hoag's object, though. The biggest problem is reproducing the galaxy's extreme symmetry. Even with high-resolution models, rings formed in simulations tend to be slightly oval, clumpy, or tilted. Small irregularities are normal because galaxies are chaotic systems. Their stars and gas respond to countless gravitational tugs from internal structures and nearby objects. Hoag's object, however, shows none of these expected distortions. Its ring is so perfectly circular that even the most precise models can't match it without artificially smoothing the data. The empty space between the core and the ring is another place where things often break. More often than not, over hundreds of millions of years, gas and stars from the ring move inward, filling the space and starting new star formation closer to the core. Very much like this, galaxies like the cartwheel have gas links that connect the outer ring to the middle. Hoag's object won't follow this trend no matter what. In real life, the gap has almost no stars at all, but in computer models, it goes away quickly unless certain conditions are met. Formation theories also run into trouble. In collision-based models, a smaller galaxy passing through a larger one can generate a ring structure via gravitational shock waves. This works well for galaxies with clumpy, uneven rings. But for Hoag's object, the simulations produce debris trails, asymmetrical arcs, or warps that we simply don't see. In resonance-based models, where internal patterns like bars create rings, the absence of any bar in Hoag's object makes the math difficult to justify. Even when the models are adapted to remove the bar, the resulting rings in the simulations tend to be unstable and fade over time. Gas composition adds another layer of complexity. Hoag's object's ring stars have a chemical makeup that doesn't match what models predict for their supposed formation scenarios. Simulations often assume that the gas forming the ring comes from the galaxy's original material or from a captured companion, but the metallicity profile, the amount of heavier elements in the stars, in Hoag's object doesn't match either of those sources neatly. When these metallicity constraints are added to the models, the probability of producing a Hoag-like ring drops dramatically. Dark matter distribution is yet another sticking point. The shape and density profile of a galaxy's dark matter halo play a huge role in determining the stability of structures like rings. In simulations, tweaking the halo to match Hoag's object's stability often results in unrealistic side effects elsewhere in the galaxy's structure. For instance, a halo dense enough to lock the ring in place can also cause the core to spin faster than observed, or lead to excessive star formation that should have left the core dustier and more irregular than it is. Even the most advanced multi-physics simulations, those that combine gravitational interactions, star formation feedback, and cosmic environment effects, can't produce a galaxy that matches all of Hoag's object's known properties at once. The models might get the ring right but fail to match the core's smoothness. Or they might create a good-looking gap but with an elliptical ring. There's always a trade-off, as if the galaxy is daring the laws of physics to replicate it perfectly. The failure of models doesn't mean that our understanding of how galaxies work is wrong, but it does show us where we still don't know enough. It's possible that Hoag's object was created under a set of initial conditions that are so uncommon that they aren't found in normal model files. Or maybe there's a physical process going on here that our present understanding of physics doesn't fully explain, like a strange relationship between dark matter and baryonic matter. Hoag's object is still a strange object in the world of computer-aided stargazing. Astronomers check to see if this strange galaxy finally shows up on the screen every time a new set of models is run. Comparisons to other ring galaxies. Most of the time, people talk about Hoag's object in the same breath as other ring galaxies, but when you put it next to its so-called relatives, the differences are clear. To really understand how rare it is, you need to look at cases like the Cartwheel Galaxy, AM 0644741, and the Lindsay-Shapley ring, whose rings formed in much more common ways. The Cartwheel Galaxy, which is about 500 million light-years away, is likely the second most well-known ring galaxy after Hoag's object. At first glance, it looks like Hoag's object. It has a bright outer ring around a fainter center. But this is only a surface similarity. The ring around the cartwheel was made when two very fast-moving galaxies crashed into each other. A smaller galaxy slammed into the larger galaxy's disk, causing shock waves that squished gas together and caused stars to form. This process left behind long, bright spokes of metal, a ring with uneven thickness, and pieces of metal that were spread out far from the main body. Hoag's object doesn't have any of these crazy traits. AM0644741, sometimes called the Lindsay-Shapley ring, is another collision product. Its ring is thick, irregular, and packed with clumps where massive star-forming regions dominate. You can see clear asymmetries caused by the uneven way the shock wave traveled through the galaxy's disk. In contrast, Hoag's object's ring is smooth, evenly bright, and so perfectly circular that no obvious collision scars can be found. This difference is crucial because even the most idealized simulations of collision rings produce some level of distortion. You can also look at polar ring galaxies, such as NGC 4650A, to see how they compare. A ring of stars and gas circles at a sharp angle to the disk of the main galaxy in these systems. This is usually because material from another galaxy was taken in. They can stay stable for billions of years, but they almost always show a clear bridge of gas, or a wavy transition zone, where the trapped matter interacts with the disk of the mother galaxy. Hoag's object doesn't have any of those things, and its ring is in the same plane as the spinning of its core. Analysts usually find trends in the metallicity, the amount of stronger elements, of other ring galaxies, that make sense in the context of how they formed. In impact rings, the stars farther out usually have more metals because they were formed from gas that was squeezed and made richer by recent starbursts. The metallicity of resonance rings is often the same as that of the inner disk. This is because the gas was pulled in by the structures of the galaxy. Hoag's object doesn't fit either pattern perfectly. Its metallicity profile is unique, and it doesn't match any of the common formation patterns seen in its cousins. Even the dynamics of Hoag's object's ring differ from those of other systems. In the Cartwheel and AM 0644 741, the ring is expanding, a direct result of the shockwave from the collision. Observations of Hoag's object, however, suggest that its ring is not expanding at all, but is instead in a long-term stable orbit around the core. This makes it more like a carefully engineered structure than the byproduct of a cosmic accident. The isolation of Hoag's object is another separating factor. Many known ring galaxies are found in environments with other nearby galaxies, increasing the chances of the kind of interactions that form rings. Hoag's object, on the other hand, sits in a relatively empty patch of space, far from any large neighbors that could have recently disturbed it. This solitude makes the idea of a collision or gas capture even harder to justify. A lot of scientists are having a hard time deciding what type of ring galaxy Hoag's object should be put in. It doesn't have the shape of an impact ring, it doesn't have the interior drivers of a resonance ring, and it's not lined up like a polar ring. Because of this, it's often put into the broad category of peculiar galaxy, which is for things that don't belong anywhere else. It's easy to see the pattern. Hoag's object is different, not because it has a ring, since many galaxies do, but because it has the wrong kind of ring. Its construction, from its perfect symmetry to its chemical makeup, can't be explained in the normal ways. The chance alignment theory. When presented with something as weird as Hoag's object, astronomers may resort to the simplest explanation. Perhaps it isn't a single peculiar galaxy at all. From our point of view, it might just look like two standard galaxies lined up exactly. This chance alignment theory says that the golden center would be one galaxy and the outer ring would be another, much farther away galaxy that looks like it wraps around the first one just by looking at it from a certain angle. On paper, this idea has a certain appeal. It would mean there's no need to invent an exotic formation scenario, no need to explain a massive empty gap, and no need to account for why the core and ring seem so different in color and age. But the moment astronomers began testing it, the theory started to collapse under its own improbability. The first problem is alignment itself. For the core and ring to look so perfectly concentric, the centers of both galaxies would have to be positioned with extreme precision along our line of sight. Even a small offset would make the ring appear lopsided or distorted. The odds of two galaxies just happening to align in this way, especially in a patch of space as sparsely populated as the one Hoag's object occupies, are staggeringly low. The second issue comes from the redshift measurements. Redshift is the stretching of light caused by the expansion of the universe, and it directly correlates to a galaxy's distance. If the core and the ring were separate galaxies, they would almost certainly have different redshifts, indicating different distances from Earth. However, when astronomers examined the spectra of both the core and the ring, they found the redshift values to be nearly identical. That means they're not just lined up in space. They're physically located at the same distance, strongly suggesting they're part of the same gravitational system. There's also the matter of the ring's dynamics. Detailed observations reveal that the stars and gas in the ring are moving in a way consistent with being bound to the core's gravity. If the ring were actually a background galaxy, its stars wouldn't care about the core's mass and wouldn't share its rotation pattern. The fact that they do tells us the core and ring are interacting in a way only possible if they belong to the same galaxy. The empty gap is another thing that goes against the idea. We would expect to see tiny signs of the galaxy's own internal structures crossing that gap if the ring came from a background galaxy. These could be spiral arms, dust lanes, or scattered star clusters that happen to stick out across the foreground core. The gap is actually totally dark, which is what we'd expect if it were really empty space and not just an area of overlapping projections. Some people have tried to save the chance alignment theory by saying that the light from the background galaxy is being bent into a ring by the core in the center. But as we've already talked about, Hoag's object has a mass that is much too small to make such a perfect Einstein ring, and the visual features don't match what we see in real lensing events. Even if you ignore all the physical evidence, the statistical odds are almost insulting to the theory's credibility. Astronomers have catalogued millions of galaxies, and while chance overlaps are not uncommon, one galaxy partially blocking another, perfect concentric alignments like this are virtually unheard of. To have one that also happens to share the same redshift, same rotation dynamics, and same isolation in space stretches the definition of coincidence past breaking. The idea of chance alignment had been mostly thrown out by professionals by the early 2000s. People sometimes still talk about it, usually when they're hearing about Hoag's object for the first time, because it seems like a cool optical trick explanation. But the more you look, the more clear it is. The ring and the core are connected and dancing in the same gravity embrace. It wasn't luck that made up Hoag's object. It was a strange thing. Spectral surprises. They don't just look at the shape of a galaxy to figure out what it's made of, they also break down its light. Scientists can read Hoag's object's fingerprints by using spectroscopy to break its light into its individual bands. This lets them figure out its chemical makeup, temperature, motion, and even how old its stars are. In most galaxies, the spectrum tells a pretty similar story from one part of the galaxy to another. The spectrum of the core and the spectrum of the ring don't match at all in Hoag's object, though. The core's spectrum is dominated by light from older, cooler stars. It shows strong absorption lines from elements like magnesium and calcium, the kind you expect from an ancient stellar population that's been quietly aging for billions of years. The relative lack of emission lines, the bright spikes that signal hot, glowing gas, confirms that there's little or no ongoing star formation in the core. This is exactly what you'd expect for a golden, elliptical-like center. The ring's spectrum, however, is a completely different story. Here, the light is bluer and hotter, with strong emission lines from hydrogen and oxygen. These lines are a sign of active, ongoing star formation, with young, massive stars flooding the surrounding gas with ultraviolet radiation. The oxygen lines also indicate that the ring's gas has been enriched by multiple generations of stars, but the enrichment level is unusual, higher than in some galaxies of similar size, but lower than you'd expect if the gas had spent billions of years recycling through the core. The fact that the core and the ring move at different speeds is one of the most surprising things that the spectral data showed. To find out how fast different parts of the galaxy are moving toward or away from us, scientists look at the Doppler changes in the spectral lines. In Hoag's object, the stars in the ring spin much faster than the stars in the core, and the two parts don't seem to be dynamically connected very well. This doesn't make sense. In most galaxies, the inner and outer parts are connected by a smooth change in wind speed. The sharp break in Hoag's object makes it seem like the ring and core may have formed in very different ways. The difference in age between the two areas is another strange thing that spectroscopy has shown. Most of the stars in the ring are only a few billion years younger than the stars in the core. In fact, it looks like the ring has been through at least two separate bursts of star formation. One was fairly recent, maybe within the last billion years, and the other happened a lot longer ago. It is still not clear why a stable ring structure would turn on star creation so quickly after the core had stopped working. The spectra also reveals something strange about the gas in the ring. Normally, the gas fueling star formation in a galaxy's outskirts either comes from the galaxy's own reservoir or is captured from intergalactic space. In both cases, the metallicity, the proportion of elements heavier than helium, follows a predictable pattern. But in Hoag's object, the metallicity gradient doesn't make sense. The ring's gas is chemically different from what you'd expect if it had come from the core, yet it's also too enriched to have come directly from pristine intergalactic gas. This mismatch deepens the mystery of where the ring's material came from. Some spectral traits are missing from both areas, which is weird. For example, the signs of shock-heated gas, which is common in galaxies that have collided or had strong gravity interactions, are weak or not present at all. This fits with other proof that Hoag's object hasn't been through a violent event recently. However, it also takes away a big possibility for how the ring formed in the first place. It's clear from these spectrum shocks that Hoag's object is more than just a strange thing to look at. It's also a chemical and dynamical puzzle. Its old quiet core and its younger star-forming ring are very different from each other, which goes against the usual evolutionary link between a galaxy's center and its edges. Like two different stories are being told at the same time, and no one is sure how they fit together. Infrared observations. Light that we can see can show us the big picture of a galaxy, but it doesn't always tell the whole story. Optical binoculars can't always see things like dust, cooler stars, and secret areas where stars are being formed. That's where findings in infrared light come in. Astronomers can see through clouds of dust, find groups of cooler stars, and find traits that optical images miss totally by looking at wavelengths that are longer. When the infrared light was shined on Hoag's object, it confirmed how strange it looked and added to the puzzle. The first surprise was the sheer lack of dust emission from the core. In most galaxies, even very old cores contain some dusty regions, either left over from past star formation or drifting in from the outer disk. Infrared wavelengths are especially good at picking up the glow of this warm dust. But in Hoag's object, the core appeared almost dust-free, reinforcing the optical impression of a pristine, untouched central region. If dust had been present at any point in the recent past, infrared detectors would have lit up with its signature, but they didn't. The ring, on the other hand, told a very different story. In infrared images, it showed strong signals from both dust and cooler, redder stars. This indicates that while the ring contains many young, hot stars visible in optical light, it also hides an older population that has cooled enough to shine more brightly in infrared. This older component suggests the ring has been around for much longer than a single starburst phase, contradicting the idea that it might be a recent, short-lived structure. The way the star-forming regions are spread out in the ring is an additional fascinating finding that the infrared data shows. The ring looks smooth in visible light, with no big lumps that stand out. But in the infrared, scientists saw small changes in light that pointed to places where new stars have heated up cooler dust. These tiny hotspots show a patchwork of activity that can't be seen with optical wavelengths. This suggests that the past of star formation is more complicated than was thought before. Infrared studies also allowed astronomers to probe the metallicity of the hidden star populations. Older, cooler stars tend to have different spectral fingerprints in the infrared compared to younger stars, and by analyzing these patterns, scientists found that some parts of the ring have chemical compositions that differ significantly from others. This hints at multiple episodes of gas inflow into the ring over time, each possibly from a different source, which would explain the patchy metallicity without invoking a major collision. A very strange discovery came from taking pictures of the empty space between the core and the ring with deep infrared light. Infrared monitors should see almost nothing in the gap if it really didn't have any stars in it. The gap did stay almost totally dark. which proved that it's not just an optical effect caused by dust blocking the light. Why is this important? Infrared pictures of other ring galaxies often show tiny bridges of stars in these kinds of gaps, but not in Hoag's object. This empty space is real and complete. Infrared data also shed light on the dynamics of the ring. By studying the motion of cooler stars and dust clouds, astronomers confirmed that the ring is in a stable, long-term orbit, not expanding like in collision-generated rings. This stability, combined with the presence of older stars in the ring, strengthens the idea that Hoag's object has maintained its peculiar configuration for billions of years. Optical telescopes had only barely picked up on this, but the infrared pictures showed a dim, long halo of scattered light beyond the ring. This halo might be the leftovers of an older, wider ring of stars, or it could be the mark of a dark matter distribution that goes far beyond the galaxy's visible parts. In either case, it's another piece in the puzzle of how a system so well balanced could have grown and survived in such a cold place. The puzzle of Hoag's object was not solved by infrared studies, but they did show that the galaxy is even stranger than it appears to be in visible light. They strengthened the belief that this is not a typical ring galaxy by finding hidden stars, proving that the gap is really empty and showing a faint outer halo. It's possible that its story involves things or situations we haven't even started to think of yet. The problem with stellar orbits. In most galaxies, we know a lot about the paths that stars take. In a spiral disk, an oval core, or an irregular system, the pull of gravity and the spread of mass cause stars to move in patterns. These patterns help astronomers guess how stars should move, and most of the time, measurements agree with the guesses. But in Hoag's object, the outer ring stars don't act the way the models say they should, and the changes aren't small enough to ignore. The first sign of trouble came when astronomers measured the orbital speeds of stars in the ring using Doppler shifts. They found that while the stars' velocities are broadly consistent with the galaxy's total mass, there are subtle, systematic deviations. Instead of following a perfectly flat rotation curve, the kind expected if dark matter is smoothly distributed around the galaxy, the speeds dip and rise slightly at intervals along the ring. This wobble is unusual for such a symmetrical structure and implies either that the mass inside the ring isn't evenly distributed or that something else is influencing the star's motion. The star's orbits seem to be very close together, which is another strange effect. In most galaxies, star paths are not all the same shape. Some are almost circular, while others are longer. Over time, gravity pulls tend to spread out stars, making this variety even greater. That being said, in Hoag's object's ring, the paths look like they are very spherical, like the stars have been locked into a nearly perfect loop. Standard models of how galaxies work don't easily explain how they can reach and keep that level of orbiting accuracy for billions of years without outside influence. Simulations of ring galaxies show that such perfect orbits are often unstable over cosmic timescales. Small perturbations, from passing dwarf galaxies, uneven gas clouds, or even internal gravitational shifts, should cause stars to drift slightly inward or outward. But in Hoag's object, there's no sign that this is happening. The ring has kept its narrow width, and the stars remain in place as if held there by an invisible guide. Even the vertical motions of the stars, tiny oscillations above and below the plane of the ring, don't fit neatly with predictions. In most galaxies, these oscillations gradually thicken a ring or disk over time. In Hoag's object, the ring's thinness suggests that vertical motions are suppressed or damped more effectively than usual. This could mean that the dark matter halo surrounding the galaxy has an unusually smooth and symmetric shape, exerting an even pull in all directions. But such a perfectly uniform halo would be rare, and it would need to match the core's mass distribution almost exactly. The gas in the ring doesn't match up with the star's paths in a unique manner. Even though the stars move in a pretty steady circle, some of the gas clouds move in or out slightly, and their speeds change in small ways that shouldn't be there if the ring were perfectly balanced. These differences show that the gas and stars aren't reacting to the galaxy's gravity in the same way. This could be because of past events or ongoing, small-scale flows of matter from outside the galaxy. The ring's steady orbit may be due to resonance, which is when the periods of the star's orbits are in a simple numerical ratio with another spinning feature, such as the core or a secret mass distribution. Stars can be shepherded into tight lanes by this type of resonance, which works a lot like how moons around our sun move planetary rings. The issue is that Hoag's object does not have any such shepherding feature, and the core moves too slowly to be the cause. The lack of orbital drift is especially puzzling when you consider the galaxy's age. If the ring has been in place for billions of years, it has survived countless potential disruptions, passing intergalactic clouds, the gravitational pull of unseen small galaxies, and even the slow reshaping of its own dark matter halo. Yet the orbits remain pristine. This level of stability hints that either Hoag's object formed in a remarkably undisturbed environment and has stayed that way, or that it's benefiting from some stabilizing mechanism we haven't yet discovered. A relic from the early universe. Galaxies do not last forever. Over billions of years they join, change, and grow. Many years of crashes, gas flows, and bursts of star formation have made most of the galaxies we see today, whether they are spirals, ellipticals, or irregulars. However, some scientists have thought, what if Hoag's object is different? If it's not the result of recent action, but rather a fossil from a very long time ago, what would that mean? This idea stems from how unusual the galaxy's structure is compared to its surroundings. Hoag's object sits in relative isolation, far from the dense galaxy clusters where most mergers and transformations happen. Its core is smooth, dust-free, and made up of older stars, features that hint at stability over billions of years. The ring, while containing younger stars now, could have been part of the galaxy for most of its existence, with periodic star formation events triggered by slow, subtle processes rather than violent encounters. It's possible that Hoag's object formed at a time when the world was very different from how it is now. In the early billion years after the Big Bang, galaxies were smaller, had more gas, and were more likely to have bursts of star formation that happened very quickly. If Hoag's object had formed in a less busy part of space, it might not have been affected by the chaotic merging that made other galaxies. It might have settled into its ring and core shape over time and stayed mostly the same. Support for this comes from the metallicity, the abundance of heavy elements, in the galaxy's stars. The core's high metallicity suggests a long history of star formation that enriched the gas early on, followed by a sharp slowdown. The ring's metallicity, meanwhile, is consistent with gas that has been processed over many billions of years, but not significantly disturbed. This is unlike younger ring galaxies, which often show signs of freshly captured, low metallicity material from outside sources. If Hoag's object really is a relic, it could also explain its nearly perfect symmetry. Galaxies that have been dynamically stable for eons have time to relax into smoother, more regular shapes. Irregularities in the orbits of stars and gas get evened out over cosmic timescales, leading to the kind of geometric precision we see in the ring. Any small distortions caused by minor gravitational nudges in the past could have been damped away long before humans ever looked through a telescope. This ancient origin theory, however, runs into a big question. How did it get the ring in the first place? The early universe was not known for producing such clean, large-scale rings without some sort of interaction. One idea is that Hoag's object could have started as a spiral galaxy whose outer arms slowly evolved into a detached ring as gas flowed outward and settled into resonance orbits. Over billions of years, the spiral arms might have faded, leaving behind the isolated ring we see now. You could also think that Hoag's object is the leftovers of a very early gas-filled merger. But since it happened so long ago, all the trash that would have been a sign of it has been swallowed or spread out. In this case, the ring might have been made by gravity waves traveling through the galaxy's disk during the merger, while the core stayed together enough to keep its identity. The jumbled pieces from such an event would become invisible over time, making the galaxy look like it hasn't been affected by anything. Many people also think that the galaxy's dark matter ring may have helped keep its old shape. If the halo is very dense, smooth, and circular, it might have acted as a gravity cushion that kept the galaxy from being distorted by tides for billions of years. This could be the reason why the ring hasn't bent or broken, even though it looks very fragile. If Hoag's object is truly a relic from the early universe, studying it could offer a rare window into a bygone era of galactic evolution. Most galaxies that formed back then have long since been reshaped beyond recognition, but Hoag's object may have escaped that fate. It could be a survivor from a time when the cosmic web was just starting to organize into the vast filaments and voids we see today. This is still just a theory because there is no direct proof of its early past, like very old stellar populations in the ring or traces of ancient gas chemistry. One thing that is certain is that if Hoag's object is a dinosaur galaxy, it has been a very well-preserved one, spinning slowly in perfect symmetry for a very long time. The statistical impossibility. In the universe, you can expect to find rare things. It's possible for strange alignments, extreme conditions, and odd forms to happen by chance in the world. But Hoag's object breaks that assumption to its limits. Astronomers have tried to figure out how likely it is that a galaxy would have a perfect ring, a perfect elliptical core, a big empty gap, matching redshifts, stable dynamics, and almost perfect symmetry. The numbers get so small that they are almost ridiculous. To begin with, ring galaxies themselves are already rare. Only about 1 in 1,000 galaxies in the local universe shows a prominent ring, and most of those are the messy, collision-formed kind. Perfect smooth rings like Hoag's object. They're so uncommon that fewer than a dozen well-confirmed examples exist in the astronomical record, and none match its size, proportion, and isolation. Then you factor in the size ratio between the ring and the core. In Hoag's object, the ring's diameter is roughly 4 times larger than the core's, and the empty gap is proportionally massive compared to other known systems. This alone places it in a category of 1. There's no other galaxy on record with such a large, clean separation between its central bulge and outer ring, without visible bridges of stars or dust. The symmetry adds another level of improbability. Cosmic structures are rarely perfect circles. Gravitational interactions, uneven star formation, and even random density fluctuations tend to warp and distort them over time. For Hoag's object to maintain such flawless geometry suggests either a unique stabilizing mechanism or an almost impossibly calm history. In statistical terms, the odds of such symmetry surviving over billions of years without disturbance are tiny, far smaller than the odds of a typical galaxy remaining undistorted for the same period. Then there's the age mismatch between the core and the ring. Most ring galaxies show either similar stellar ages across both regions, if formed together, or clear evidence of a recent event that rejuvenated one part. Hoag's object's stark difference, an ancient quiescent core surrounded by a still active ring, means whatever formed it had to not only create this arrangement, but also keep it intact for an extremely long time. Modeling the odds of that sequence of events only shrinks the probability further. If you treat each unusual feature of Hoag's object as an independent factor, perfect symmetry, large empty gap, old core with young ring, absence of collision debris, isolation in space, stable orbits, and multiply the probabilities together, the result becomes so small that it's hard to express in ordinary numbers. Even conservative estimates suggest odds far less than 1 in a billion for a galaxy to tick every one of these boxes at random. Some astronomers caution that multiplying probabilities like this can be misleading because the features might not be entirely independent. For example, a particularly calm formation environment might increase the odds of both symmetry and stability at the same time. But even when allowing for these correlations, the odds remain shockingly low. It's as if the galaxy is playing by a different set of rules than the rest of the cosmos. The improbability has led some researchers to wonder if our surveys are missing other Hoag-like galaxies. hidden in distant or poorly imaged regions. But so far, deeper sky scans have only reinforced its uniqueness. There are a handful of partial lookalikes, galaxies with bright rings and faint centers, but none have the same proportions, emptiness, or undisturbed structure. Hoag's object is a warning to both statisticians and astronomers that the world sometimes has outliers that are so far out of the norm that they make the models themselves look wrong. Whatever theory you have about how galaxies form says that something like Hoag's object should almost never happen, but it does. The theory needs to be rethought. This statistical impossibility doesn't mean the galaxy is magical or doesn't follow the rules of physics, but it does mean there are things going on that we don't fully understand or haven't seen happen anywhere else yet. Not only is Hoag's object possibly rare, it may also be the only example of a galaxy creation route that was more common in the past. This would make it both a time capsule and a statistical outlier. Hubble's zoom-in mystery. When the Hubble Space Telescope turned its powerful optics towards Hoag's object in 2002, the goal was to capture the most detailed image yet of its pristine ring and golden core. What astronomers didn't expect was to find something unusual hiding in plain sight. A tiny, faint galaxy sitting inside the vast starless gap between the core and the ring. It's easy to miss the thing at first look. It's small, dim, and almost perfectly lined up with Hoag's object, like someone put it there on purpose. It looks like a small spiral galaxy in the famous Hubble picture, where it stands out as a long smudge in the middle of an otherwise empty space. This quickly made people wonder if it had anything to do with Hoag's object or if it was just another cosmic chance. The discovery led to a flurry of speculation. If the small galaxy was gravitationally bound to Hoag's object, it could potentially offer clues about the ring's origin. For example, it might be a remnant core of another galaxy that once interacted with Hoag's object, possibly triggering the formation of the ring. But if that were true, astronomers would expect to see some tidal debris, faint streams of stars or gas connecting the two. Careful imaging, however, revealed nothing of the sort. The gap between the small galaxy and the inner edge of the ring remains truly empty. Spectroscopic analysis provided the next big clue. By measuring the redshift of the small galaxy's light, astronomers determined that it is not at the same distance as Hoag's object. Instead, it lies far behind it, meaning it's just a background galaxy seen through the ring's inner void. This neatly explains why there's no sign of interaction between the two, but it also makes the alignment seem incredibly coincidental. As a matter of fact, some scientists said that when seen from Earth, a few background galaxies will always be seen inside other galaxies. Space is very big, and lines of sight cross over time. But for one to show up so exactly in the middle of Hoag's object's ring, especially in a galaxy that is so symmetrical and far away from everything else, is something that even experienced experts find strange. The background galaxy's shape also sparked curiosity. It appears to be a barred spiral, a type of galaxy with a central bar of stars and two sweeping arms, seen almost face-on. This means its round shape in the image mirrors the circular geometry of Hoag's object's ring, making the alignment all the more striking. To the casual observer, it might look like a galaxy within a galaxy, even though they're separated by vast distances. The Hubble zoom-in on the core and gap region not only revealed this background galaxy, but also allowed astronomers to confirm just how clean the empty space between the core and ring truly is. Even in Hubble's incredible resolution, no faint star clusters, gas clouds, or dust lanes fill the gap. This absence reinforces the idea that the ring and core are dynamically and structurally separate, with no material linking them, a fact that continues to challenge formation theories. Since then, the tiny galaxy in the gap has become a popular thing to talk about when Hubble's pictures are shown. For the public, it makes the sky even stranger by adding a silly cosmic bullseye feature to it. For scientists, it's a warning that the universe is three-dimensional and that redshift readings are important for telling the difference between real connections and optical illusions. The background galaxy doesn't explain Hoag's object and doesn't seem to have anything to do with its structure. But the fact that it exists shows how optical positions in space can be so accurate that they almost look like they were planned. It kind of adds to the improbability of Hoag's object, as if one of the strangest galaxies ever found needed a small, strange thing hidden in the middle of it to make things even stranger. The problem with tidal forces. Studying tidal forces, the stretching and pulling caused by gravity from other nearby large objects, is one of the easiest ways for scientists to see if the structure of a galaxy can last for billions of years. These forces are a big part of how most ring galaxies change shape, twist, or lose their unity over time. But Hoag's object doesn't seem to follow these rules. Even though it has a thin, separated ring and a huge empty space between them, it doesn't seem to be bent, stretched, or disturbed by the pulls of gravity from its surroundings. Normally, galaxies are never truly alone. Even in seemingly empty parts of the universe, they are part of larger gravitational networks that include dwarf companions, nearby spirals or ellipticals, and the overarching pull of galaxy groups and clusters. These neighbors, whether close or tens of millions of light years away, exert tidal forces that can subtly distort shapes over time. Rings can become oval, spiral arms can twist, and cores can become lopsided. The more fragile a structure is, the more quickly tidal forces can leave their mark. Hoag's object, however, sits in near-perfect isolation. Surveys of the region around it have found no large galaxies within a threatening range, and even small companions are rare. This extreme solitude means tidal forces from outside are already weaker than average. But isolation alone doesn't explain everything. Because even without nearby galaxies, the cosmic web itself exerts a diffuse but measurable tidal influence. In most simulations, a galaxy with such a large and empty inner gap should be more vulnerable to these subtle forces. With so little material between the core and ring to stabilize the gravitational field, the outer ring ought to be more easily perturbed. Over hundreds of millions of years, it could be expected to drift inward, warp slightly, or even fragment into clumps. Yet observations show the ring's shape is as perfect as ever, with no detectable warping or asymmetry. There's another layer to the puzzle: the interaction between the core's gravity and the ring's mass. In many galaxies, the stars and gas in a ring interact gravitationally with the central bulge, leading to complex orbital patterns. If the balance isn't perfect, tidal stresses from the core itself can cause parts of the ring to spread outward or collapse inward. For Hoag's object, the balance seems uncannily precise, as if the core and ring have been locked in a long-term gravitational truce. This stability raises the possibility that the galaxy's dark matter halo is playing a key role. If the halo is unusually smooth, spherical, and evenly distributed, it could create a perfectly symmetrical gravitational environment that shields the ring from tidal distortion. Such a halo would essentially wrap the galaxy in a protective bubble, keeping the ring's orbit stable despite the lack of material in the gap. However, halos this uniform are thought to be rare, making Hoag's object even more of an outlier. The lack of tidal disruption also challenges the idea that Hoag's object is the result of a past collision. If it had formed from an interaction with another galaxy, tidal forces from that event should have left some lasting imprint: a faint trail of stars, an off-center core, or uneven density in the ring. The total absence of these features suggests that if a collision did occur, it must have been so long ago, or so gentle, that all traces have been erased, a scenario that is itself statistically unlikely. Astronomers often find that tidal forces should have changed the shape of Hoag's object over cosmic timescales if it wasn't for some kind of ongoing sustaining force. These changes haven't happened in real life, which means that either important parts of physics are missing from the models, or Hoag's object is in a very rare gravitational sweet spot. Hidden mass discrepancy. It's not as easy as adding up all the stars we can see to figure out how heavy a galaxy is. The vast majority of a galaxy's mass is hidden from view, either in dark matter or in gas and dust, that don't look bright to the naked eye. Scientists can tell a galaxy's total mass by how fast its stars and gas are moving. The difference between this mass and the mass of the visible matter is usually big, but expected. That's not what Hoag's object does. The difference between what we think its mass is and what we see as its light is so strange that it makes us wonder if we're even measuring it right. The starting point for mass measurement is the galaxy's rotation curve, a plot of how fast stars and gas move at different distances from the center. In most galaxies, the rotation speeds stay high, even far from the core, suggesting the presence of a large dark matter halo. For Hoag's object, the speeds in the ring are consistent with there being plenty of extra mass beyond what's visible. However, when astronomers estimate the mass of the stars and gas we can see, the numbers don't quite line up with the expected ratio. Hoag's object seems to have more total mass than the brightness of its stars suggests, but also less dark matter than would normally be required to hold such a large, thin ring together for billions of years. This puts it in a strange middle zone, where neither a standard dark matter model nor a purely baryonic, normal matter explanation fits cleanly. Many of the galaxy's missing visible mass might be stuck in dim, low-mass stars, according to one theory. If these stars are old and bright, they give off very little light, making them hard to find. If there are a lot of these faint stars in the ring, along with its younger, brighter stars, they could make the galaxy heavier without making it brighter overall. Studies that use infrared light have given us hints about this secret community, but not enough to completely fill in the blanks. It's also viable that the galaxy has a lot of cold gas that doesn't give off much light at the wavelengths that are usually used to test hydrogen content. The 21 centimeter radio line is generally used to find neutral hydrogen, but the gas might not be picked up if it is very cold or stuck in molecular form. This dark gas might be adding to the galaxy's pull on us, even though it doesn't show up in regular measurements. Some researchers have also considered whether the dark matter halo of Hoag's object might be shaped differently from the halos in other galaxies. If the halo is more concentrated toward the ring, rather than spread evenly around the galaxy, it could account for the ring's stability without requiring as much total dark matter. Such a configuration, however, is rarely seen in simulations, which tend to produce smoother halos unless influenced by very specific formation events. The hidden mass problem becomes even stranger when you account for the galaxy's isolation. Without nearby galaxies to steal or share mass with, Hoag's object's mass distribution should be relatively straightforward. Yet the measurements continue to resist neat classification. Some teams have suggested that our standard assumptions about the relationship between light and mass might simply not apply here, that the processes that formed Hoag's object gave it a fundamentally different mass-to-light ratio than most galaxies. This could mean that Hoag's object is more than just a strange structure if it's true. It could also mean that our models of how galaxies form are missing an important variable. This is especially true when it comes to how mass is spread between stars, gas, and dark matter. It's possible that galaxies can form with dark matter halos that lock in matter in strange ways, creating the stable symmetric rings we see here. Could it be transient? Galaxies' time is not frozen. It could be millions or billions of years, but their forms, structures, and star populations change over time. Some shapes, like classic spirals or giant ellipticals, are pretty stable and stay the same for very long periods of time in the universe. Others are temporary and can only be seen for a short time before they are changed by gravity. This makes me wonder if Hoag's object is one of these short-lived phases, a brief arrangement in the universe that was caught at just the right time. The idea comes from the fact that Hoag's object's ring might not be able to keep its shape forever, even though it seems fixed right now. Computer models of ring galaxies, especially ones where the core and ring don't seem to be connected, often show that the ring moves inward or spreads out over time. If the stars in Hoag's object's ring move slowly toward the gap or out into space, the ring might lose its perfect balance. If that's true, then we might be seeing the galaxy during a sweet spot in its evolution, long enough after its formation for the ring to settle into its clean shape, but before the forces that disrupt such structures have fully taken hold. This window might last only a few 100 million years, a blink compared to the galaxy's total age, which would make catching it now a stroke of astronomical luck. Using a form of the transient theory, the ring could be a wave left over from a disturbance that happened a long time ago. Something, maybe a small galaxy or a burst of star formation inside the galaxy, caused a gravity ripple that pushed gas and stars outward in a circle. The wave would get smaller over time, the ring would lose its shape, and the stars would spread out. If Hoag's object is in the middle of that process, we might be seeing a phase that will soon end. The galaxy might also be briefly taking in gas from its surroundings. If a thin, long cloud of gas fell toward Hoag's object in the past, it could have been caught in a stable orbit that is now helping new stars form in the ring. That gas will run out eventually, the birth of new stars will slow down, and the ring will become less bright, so it won't stand out as a perfect halo. The transient idea also connects to the age difference between the core and the ring. If the ring stars are relatively young compared to the core, then this current configuration can't have been in place for the galaxy's entire history. That means the ring either formed recently or was rejuvenated by a fresh influx of material. In either case, the clock would already be ticking for how long it will remain in its present form. What makes this theory compelling is that many of the features that make Hoag's object so strange, the sharp separation between ring and core, the absence of connecting structures, the perfect symmetry, might simply be side effects of catching it during this rare, short-lived stage. If we came back in 1 billion years, it might look completely different, with the ring dispersed into a faint haze or drawn inward toward the core. On the other hand, the transient explanation faces its own challenges. For one, the ring's stability appears unusually high for something that's supposed to be temporary. Measurements of the star's motions suggest that the ring is not in immediate danger of falling apart, which means the short-lived window might not be as short as this theory requires. Moreover, no clear evidence of the triggering event, such as leftover debris or distorted gas clouds, has been found. We are very fortunate to be able to see Hoag's object right now if it is indeed temporary. It also means that there may be other galaxies like it, but at any given time, only a few would be visible in this phase. This could be why scientists haven't found many close matches. There aren't many chances to find one at the right time. Why Hoag's object still has no consensus. Over time, puzzles in science tend to get less mysterious. Objects that were once hard to explain generally fit into existing theories as tools get better, models get better, and measurements get more accurate. But that trend has not been followed by Hoag's object. It is still one of the most debated galaxies, even after decades of research. This isn't because we don't have enough information, it's because the information doesn't fit nicely into any one theory. The problem isn't that scientists have no theories. In fact, they have several: collision models, resonance wave models, ancient relic scenarios, even rare dark matter configurations. The issue is that every theory explains some features of Hoag's object while contradicting others. The collision idea can explain the separation between the core and the ring, but not the total lack of debris. Resonance models can explain the symmetry, but they struggle to account for the age difference between the core and the ring. The relic from the early universe theory works for the core's properties, but not for the ring's ongoing star formation. This partial fit problem has led to a kind of scientific stalemate. Teams often pick the model they find most promising, adjust it to explain one or two of Hoag's object's strangest traits, and end up with a result that still leaves unanswered questions. The galaxy has essentially become a stress test for formation theories. If your model can explain Hoag's object in full, it's probably robust enough to explain almost anything. So far, no model has passed. Not only is Hoag's object alone, but it's also very hard. Astronomers could look for trends and shared histories by comparing dozens of galaxies that are very much the same. But real things that look like Hoag are so uncommon that we can't make a mathematical picture. Every time scientists think they've found a galaxy like ours, a closer look shows that it's not quite the same. For example, the ring might be curved, the core might be off, or the gap might be full of faint junk. Technology has helped us learn more about Hoag's object, but it hasn't delivered the knockout evidence needed to end the debate. Hubble's high-resolution images in 2002 showed the galaxy in stunning detail, but also deepened the mystery by confirming its near-perfect symmetry and emptiness. Radio and infrared surveys have given us clues about its gas content and hidden stars. Yet none of these findings have been decisive enough to crown a single theory as correct. It's not just a technical problem that there isn't agreement. It's also a moral one. Astronomers are used to working within theories that explain most galaxies as the result of common cosmic processes, such as gravity, merging galaxies, accretion, and cycles of star formation inside galaxies. The unique features of Hoag's object make us think that either we're missing a rare but normal way for galaxies to form, or we need to rethink how adaptable our galaxy models are. Neither result makes you feel good. Some experts think the answer might be somewhere that can't be seen. Extreme ultraviolet, X-rays, or even gravitational waves could be used to see more about how the galaxy has changed over time, or find patterns in its dark matter ring that have been hidden. Others think that the next generation of telescopes, such as the Extremely Large Telescope or the Nancy Grace Roman Space Telescope, will be able to pick up on very faint objects or small changes that could help us figure out where they came from. For now, Hoag's object remains a case study in scientific patience. It's a reminder that not all puzzles can be solved quickly, even in an age of rapid technological advancement. The galaxy floats in its cosmic isolation, seemingly aware that it's the subject of decades-long arguments among Earth's astronomers, and offering no new hints to break the tie. Hoag's object is still a case study in science patience for now. It serves as a warning that even in this age of fast technological progress, not all puzzles can be solved right away. As it floats in space by itself, the galaxy seems to be aware that it has been the subject of decades-long arguments among scientists on Earth, but it doesn't offer any new information to break the tie. And so Hoag's object remains out there, a lonely, perfect ring in the vast dark, daring us to explain it and defying every answer we come up with. Maybe one day we'll crack its code, or maybe it's the universe's way of reminding us that some mysteries are meant to last. If you enjoyed diving into this cosmic enigma, make sure to like, subscribe, and share your thoughts in the comments below. Only on Beyond Horizons.